Good morning, guys. I welcome you all on this wonderful platform that is BYJU'S exam prep. So, guys, today is a very important session in non-tech Marathon series. And today's subject is going to be material science. Me and Ashutosh sir would be taking that. And as you will be aware of this subject, that this subject is consisting of two parts from two different branches. Like it is having a part from mechanical, that is crystal structure, crystal defects. Then it is having strengthening mechanism, iron carbon diagrams, and that what is triple D diagram and all. And then it is also having second part which is related to more about electrical, and there the topics are electrical property, magnetic properties. Okay, so there are atomic structure, all those kind of things are there. And guys, the weightage of this subject have been very good from the paper one when they have started in 2017. If you see last 5 to 6 year record, it have been very good for material science. Just last year weightage was slightly lesser. So guys, we are starting the session and we will be covering the conceptual part also, as well as some question and in a quick manner, so that you get a good revision today. Okay, so we are starting, guys, without wasting the time. So guys, I'm having around 10 plus years of experience and today's subject is going to be material science. Before we start, I would like to tell you a very important thing, that if any of your junior is thinking of preparing for GATE 2024, then there is a very important mega workshop that is on how to ace GATE 2024 in first attempt. And guys, that will be taken by Abhinav Negi sir, and it will be on 14th of February. Yes, your favorite day. And the timing will be 7:30 p.m. Okay, so this is very important thing. Yes, Pinky, good morning. So now we are starting the session, guys. Now we are starting the session. So guys, before we start the material science part, first of all, I would like to tell you a very important thing that is said to be property. Okay, so actually there are two types of property which you need to study here. One is mechanical, other is electrical and magnetic. So we will be studying all these types of properties. But when we say about property, कि property होती क्या है, then what will be the definition of property? सबसे पहले उसकी बात करते हैं. हाँ जी, yes, अनिर्बन नाथ, गुड मॉर्निंग डियर. सो जब हम बात करते हैं प्रॉपर्टी होती क्या है, जनरली जब भी मैं स्टूडेंट से पूछता हूं तो स्टूडेंट सेज दैट सर प्रॉपर्टी इज समथिंग विच कैन बी मेजर्ड. सो आई वुड लाइक टू से दैट वो डेफिनेशन आधी अधूरी है. When we are talking about the complete definition of property, it is defined as quantitative indices. Quantitative indices एक नंबर को कहा जाता है, जैसे मैंने कहा 210. Okay, so quantitative indices given to the behavior of a material whenever it is subjected to some external loading. So my dear, whenever some material is getting subjected to external loading, at that point its behavior is shown with some number that is given the name of property. Like we are going to say strength of a material, we are going to say toughness of material, we are going to say hardness of a material. So guys, all these are coming under the properties. Okay, so guys, now the point is on which thing property will be depending. Actually, if I tell you a very basic table, what we expect from material is good functional characteristics. We always are looking for good functional characteristic, which will be definitely depending on the properties. Properties are somewhere depending on the structures, and structures are depending on what? Structures will be depending on the things like manufacturing process, Structure also depend upon something called as heat treatment. So guys, all these things we are going to see today. So you know, every component, हर component अलग अलग तरीके से बनाया जाता है, और अगर हर कंपोनेंट अलग अलग तरीके से बनाया जाता है तो वो कैसे बनाया गया उस बात पे उसकी प्रॉपर्टीज भी डिपेंड करती हैं. और गाइस, एट द सेम टाइम अगर उसके अंदर कोई एलॉय एलिमेंट डालेंगे तो उस पर भी उसकी प्रॉपर्टीज डिपेंड करेंगी. तो प्रॉपर्टीज बहुत सारे फैक्टर्स पर डिपेंड करती है. तो अब हम बात करते हैं सबसे पहले स्ट्रक्चर की. तो स्ट्रक्चर 3 लेवल्स की होते हैं. पहला लेवल ऑफ स्ट्रक्चर होता है मैक्रो स्ट्रक्चर, दूसरा होता है माइक्रो स्ट्रक्चर, तीसरा होता है क्रिस्टल स्ट्रक्चर. सो व्हेन वी आर टॉकिंग अबाउट मैक्रो स्ट्रक्चर क्या है? सो माय डियर, मैक्रो स्ट्रक्चर वो है जो हम नंगी आंखों से देखते हैं, मींस विदाउट द यूज ऑफ माइक्रोस्कोप। पर अगर आपको आदत ही है कि माइक्रोस्कोप से ही देखना है, तो माइक्रोस्कोप से भी अगर आप 100 से कम जूम लेवल रखते हो तो जिस स्ट्रक्चर को आप ऑब्जर्व करेंगे उसी स्ट्रक्चर का नाम होता है मैक्रो स्ट्रक्चर। तो माय डियर, अगर आप 100 से कम का जूम लेवल रखोगे तो उसको बोलते हैं मैक्रो स्ट्रक्चर, और अगर आप माइक्रोस्कोप से देखो और 100 से ज्यादा का जूम लेवल रखो तो उसको बोलेंगे माइक्रो स्ट्रक्चर। और माय डियर, अगर हम बात करें क्रिस्टल स्ट्रक्चर की, तो इसको कैसे देखेंगे? माइक्रोस्कोप से, नंगी आंखों से? कैसे? एनीबॉडी इसको कैसे देखेंगे? क्रिस्टल स्ट्रक्चर कैसे दिखाई देगा? आपको बता दिया मैंने कि मैक्रो स्ट्रक्चर इज just wait guys, just wait. हेलो, हाँ जी, मैं अभी बाहर हूँ, कल मिलूंगा आपको। Okay guys, sorry for the disturbance. Okay guys, so we are going to continue now. So as I said guys, when we are talking about, okay, psi x-ray, बहुत ही बढ़िया, psi have answered it. So guys, when we are talking about the crystal structure cannot be seen. Crystal structure you cannot see from eyes, you cannot see from microscope. Crystal structures are observed under X-ray diffraction experiment. So when we are going to perform X-ray diffraction experiment, then you can tell that which type of crystal structure will be, and that cannot be seen, that can only be observed, क्योंकि ये बहुत ही छोटा होता है। It is the smallest out of all, इसीलिए ये दिखाई नहीं देता। अब आप सोच रहे होंगे सर मैक्रो स्ट्रक्चर देखने के फायदे क्या होंगे? मैक्रो स्ट्रक्चर देख के आपको सरफेस प्रॉपर्टी पता लग जाएगी। जैसे आपने देखा एक मटेरियल में ऐसे नोच था, तो आप देख के बता पाओगे कि इस मटेरियल की डक्टिलिटी कम होगी। हाँ, डक्टिलिटी वही है जिससे रोड वायर में कन्वर्ट होती है, वही डक्टिलिटी। तो माय डियर, अब अगर हम बात करें, आपने किसी सरफेस को देखा और उस सरफेस में ऐसे शार्प कॉर्नर बने हुए थे, एरिया का जब चेंज हो रहा था तो शार्प कॉर्नर बने हुए थे, तो ये देख के आपको पता लगेगा कि ये मटेरियल का फटीग फेलियर जल्दी हो जाएगा। तो इस तरह से आप सरफेस प्रॉपर्टी का अंदाजा लगा सकते हो। माइक्रो स्ट्रक्चर से हमको पता लगता है ग्रेन के बारे में, हमको पता लगता है ग्रेन बाउंड्रीज के बारे में, हमको पता लगता है ग्रेन ओरिएंटेशन के बारे में। तो ये सारी चीजें हमको कौन बताता है? माइक्रो स्ट्रक्चर। सो माय डियर, हमने देखा मैक्रो, माइक्रो और क्रिस्टल। अब हमारे सिलेबस में जो हमको मटेरियल साइंस में पढ़ना है वो मेजरली क्रिस्टल स्ट्रक्चर को पढ़ना है। तो अगर हम क्रिस्टल स्ट्रक्चर की बात करेंगे माय डियर, तो मैक्रो की तो मैं पहले ही बता चुका हूं कि जूम लेवल जो है वो 100 टाइम्स से कम होना चाहिए। फिर मैंने कहा माइक्रो स्ट्रक्चर की बात करें तो मोर देन 100 टाइम्स होना चाहिए। अब बात करेंगे इंजीनियरिंग मटीरियल, जहां पे क्रिस्टल स्ट्रक्चर का जिक्र होगा। जब हम इंजीनियरिंग मटीरियल्स की बात करते हैं तो उनको दो पार्ट्स में हम डिवाइड करते हैं। पहला पार्ट होता है क्रिस्टलाइन और दूसरा होता है एमोर्फस। सभी लोग समझ पा रहे हैं? हिंदी इज कंफर्टेबल फॉर एवरीवन? ओके, इफ anyone have any problem you can tell me. Okay, we can convert the language in English also, whatever you prefer. So guys, जब हम बात करते हैं इंजीनियरिंग मटेरियल की, इसको दो टाइप्स में हम बात करेंगे, पहला क्रिस्टलाइन और दूसरा एमोर्फस। तो माय डियर, क्रिस्टलाइन क्या होता है और एमोर्फस क्या होता है आपने बचपन से पढ़ा है, तो आपने रटा होगा 3D लॉन्ग रेंज पीरियोडिसिटी, 3D लॉन्ग रेंज पीरियोडिसिटी। जी हाँ, तो अगर कोई मटेरियल 3 डायमेंशन में दूर दूर तक पीरियोडिसिटी मतलब रिपीटेशन शो करता है, या तो एटम्स की, या तो मॉलिक्यूल्स की, या तो आयंस की, तो ऐसे मटेरियल को हम बोलते हैं क्रिस्टल स्ट्रक्चर। ओके ओके ओके, आई विल बी टीचिंग इन इंग्लिश नाउ। ग्रेट ग्रेट ग्रेट। सो माय डियर, जब हम whenever we are talking about crystalline, so my dear, we are going to say that a material which will be having 3D long range periodicity of atoms, okay, or molecules or ions. So wherever I will see in 3 dimension, I will feel the repetition of either atoms or molecules or ions, and that thing is given the name of crystalline material. So my dear, when we are going to see the 3D long range periodicity of atoms, they are atomic solids, and the name of atomic solids are metals. Similarly, when we have 3D long range periodicity of molecules, they are said to be molecular solids, and that molecular solids are nothing but polymers. Similarly, if we are going to have 3D long range periodicity of ions, they are said to be ionic solids and they are nothing but ceramics. So my dear, all these are coming in category of crystalline material. And if you do not get the 3D long range periodicity of atoms, molecules and ions, then whatever the structure you will be getting, it is said to be amorphous. All these things in the classes, when we have enough time, when we teach this subject for 40 hours, there we go with the good stories by which you are very easily remembering all the things. But here, as it is a marathon where we need to complete it in 5-6 hours, I will be going for the important point which will be coming in exam. Okay, so don't judge with that. Okay, as I said, so here we will be going with those points which are directly coming in paper, because this is clearly exam oriented session. So let us move further, guys. So which do not exhibit 3D long range periodicity are said to be amorphous. Some people are saying the example of amorphous is glass, quartz. Yes, they are correct. But my dear, yes, even metals can be amorphous. That all will be depending on the cooling rates. If we are going to provide very high cooling rates, then metal also will be converted into metal glasses and they will also be amorphous in nature. So yes, even metallic glasses are possible. So all this is the story of the cooling rate, that when you have a molten metal, if very high cooling rates will be provided, material will not be able to completely become crystalline. It will be showing the amorphous behavior. Now my dear, I already told you any material can be both crystalline or amorphous depending on the cooling rate. Then my dear, we have already defined 3 types of crystalline structures. Now I would be telling you about what is crystal structure. We have seen Sai Kumar, there is only one difference actually. As I already told you that this is the common part for mechanical. So as you are a mechanical student, you may have seen that technical part for mechanical part is going to be same. Okay. The only difference is in the type of question. Here the questions are more of theoretical types. Okay, and in GATE the questions are more of numerical types. That is the difference. Second difference is there is one extra part, that is electrical properties, magnetic properties, that is not in the GATE syllabus but it is there in the ESE syllabus. That will be covered at the end, second part. Okay, means after me. Okay, so guys, next we are talking about the crystal structure. So when we are talking about the crystal structure, crystal structures are observed by X-ray diffraction experiment. So I would like to say, if we are going to see the crystal structure, in a crystal structure there are 2 things. In a crystal structure there are 2 things. First thing is said to be the crystal system. First thing is said to be the crystal system. And guys, the second thing is going to be the brevis lattice. Second thing is said to be the brevis lattice. And if we are going to say all total whatever the materials are available in this universe, they all are covered in 7 types of crystal systems and 14 types of brevis lattice. So my dear, if you want to know what is crystal system, what is brevis lattice, crystal system will be telling you about size and shape of the unit cell. Size and shape of unit cell. Size and shape of unit cell. And my dear, brevis lattice will be telling you about the atomic arrangement. So when we are going to say this, I will be giving you an example that in your house or home, you would be having some number of rooms, some halls, some kitchen, some toilet, bathrooms would be there. So that shape and size of your home or house will be coming under the crystal system. And in that home or house, how you peoples are living, that in one room 1 person, in second room 2 person, like that. So that is said to be brevis lattice, that is atomic arrangement. Very good, Pogati, bahut hi badhiya. So this is what we are going to talk about. Okay. So guys, when we are talking about the crystal system, that will be depending on the lattice parameter, which are A, B and C. It will be depending on the interaxial angles, that is alpha, beta and gamma. And guys, X, Y, Z are said to be crystallographic axis. So on these dimensions, this crystal system will be depending. and how atoms are arranged here, whether atoms are present on the corners or atoms are present on the body center or atoms are present on the face center. Based on that, we will be saying the brevis lattice will be defined. Moving further, guys. So I already told you what is crystal system, what is brevis lattice. Now you may have a question, sir, why not all the materials shows the same crystal system and same brevis lattice? Why they show different crystal system and different brevis lattice? So guys, the answer to that is, when we are talking about crystal system and brevis lattice, the point is, like, if I ask you now, all of you are sitting in the same way or different way. Like, some of you may be just laying down on the bed and looking at the session like that. You may be sitting like that. Some of you may be standing and just walking and watching the lecture. So why that kind of differences? Because everyone, how he will feel comfortable, will follow the same. Similarly, based on the atomic radii, how atoms and molecules are going to be feel comfortable. Comfortable means minimum potential energy state. Based on that, they will be taking some shape or size or some crystal system or some brevis lattice. That is why, because of different sizes, because of different atomic radius, different materials are going to have different crystal structures. Okay, so that is the reason for that. Now, my dear, we will go for some basic definitions. So, my dear, as you know that 3D long range periodicity of atoms, molecules and ions is said to be crystallinity. So, unit cell is that smallest group of atom which is going to be repeated for infinite number of times in 3 crystallographic axes. Then, my dear, that smallest group of atom is said to be unit cell. Similarly, my dear, what is crystal or line lattice? In reality, the atoms are present like this, because when we are talking about atoms, they are always touching like this. Okay, but my dear, in 2-dimensional it is easy to recognize, but when they will be present in 3-dimension, it is very difficult to do the calculation with the atoms present as a sphere. So what we do is, to make the calculations easier, we always join the centers of the atom. And when we join the centers of atom, we are getting some lines. And guys, if we are going to make just the lines without the atoms like this, you will be having a 3D big giant structure of unit cells, and you will be having it in 3-dimensional like this. So that 3-dimensional structure is given the name of crystal or line lattice. But mind it, line are made by us. Lines are made by humans. Lines are not something which are actually seen in the structures. They are just made for the calculation purpose. Maniket, good morning, dear. Moving further, guys. Now we will be talking about the space lattice, my dear. Now, what is space lattice? So when we are talking about the space lattice, we already know that atoms are present as a sphere. They are always touching with each other. But my dear, to show them conveniently, we are showing them with the lines like this. Even if we go with some good presentation, you can show the atoms on the corners. Actually, atoms are touching, but we will be showing them with the dots. That is also one of the presentation. Now, if you show these dots without the lines, if I just remove the lines and leave the dots only, you will be having this type of structure. So that is said to be the space lattice. Without lines, if you show the atoms by dots, okay, or you can say you are representing the centers of the atom, it is said to be space lattice. It is not a good view, because by looking at this, you will not be able to know in which plane the atom is actually present. So that is why this is not a good view. Next is the primitive cell. Primitive cell is a simple cubic cell. Simple cubic means simple for 8 corner atoms. When all the corners have 1 atom each, we call that structure as simple. And cubic is because A, B, C, which are lattice parameter, are equal. Interaxial angle are equal. So when, my dear, we have this kind of geometrical property, we call this as cubic. So cubic means these property, simple means 8 corner atom. So that wonderful, the very first basic unit cell is given the name of primitive cell. Moving further, my dear, moving further. I already told you there are a total of 7 crystal system and 14 brevis lattice. So guys, here I have shown those 7 crystal system: cubic, tetragonal, orthorhombic, monoclinic, triclinic, hexagonal, trigonal, rhombohedral. And guys, out of these, when we are talking about, generally monoclinic, triclinic are used in the application of medical. So those students who are going for medical sciences, they need to study these types of material. Similarly, there are some which are useful in civil engineering application. There are some which are useful in mechanical engineering application. There are some which are useful in electrical and electronics. So different branches have different material. And guys, these all are the 7 system in which all those materials are coming. These are the properties, the relationship of those 7 crystal systems. Okay, so if you want, otherwise I will be giving you the PDF after the session, but you need not to remember this whole question, have never come from this kind of thing. But yes, you must remember all the 7 systems, all the brevis lattice. Okay, so I would like to say, what are the various types of atomic arrangement? So when we are talking about atomic arrangement, the first type of atomic arrangement is simple. Simple is that kind of atomic arrangement where we will be having 8 corner atoms. When we will be having 8 corner atoms, that kind of structure is said to be the simple one. Second, my dear, whenever we are talking about, is said to be the body centered. So what is body centered? If we are going to have 8 corner atom plus 1 body center atom, then that structure is said to be body center cubic. Then my dear, third one is said to be the face center cubic. Face center cubic is having 8 corner atom plus 6 face center atoms. So guys, this is the third one, and fourth one is end centered. So end center means you will be having 8 corner atom and any 2 ends will be having the atoms, that is end center atom. Okay, so guys, as I already told you, in our syllabus we need to more concentrate on BCC and FCC. Okay, sorry, BC and FC, that is body center and face centered. Now how the name will be defined? If we are talking about cubic, then face centered cubic, body centered cubic. If we are talking about orthorhombic, then body center orthorhombic. So orthorhombic will tell you system, and this will be telling you the arrangement of the atoms. This is how the things are defined, my dear. Moving further, so guys, now we are coming to the characteristics, and questions are coming from the characteristics. As I already told you guys, this session is to maximize your marks. This session is to give you everything quickly. So rather than going for all the proof, I will be directly telling you the properties. If we are talking about A to R ratio, then for simple cubic, A to R ratio will be like A is equals to 2 times of radius. Okay. When we are talking about body centered cubic, for that A is 4R by root 3. Now what is this? What is A? A is the lattice parameter. R is the atomic radius. Okay. So my dear, when we are talking about the face centered cubic, then you will be getting A is equals to 2 root 2R. Okay. So I can derive it also in the previous marathon of material science. I derived this. But dear, at the end, you just need to remember it. HCP also I will tell you Pogati Ganesh, don't worry. So now this is first I am telling you about the cubic structures. So my dear, this is about the cubic. Okay. So when we are talking about, there is one more structure, HCP, hexagonal close pack. That also I will show you. For that also A is equals to 2R. So guys, this is the A to R ratio. What A to R ratio is going to tell us? Actually, when you will be changing the crystal structure from BCC to FCC to HCP to simple, every time A to R ratio is changing. A to R ratio is somewhere deciding the density factor. So if, my dear, you will be changing from simple cubic to BCC to FCC to HCP, the density is the property which will be depending on A to R ratio. Okay. So my dear, I can show you the figures also if you want. So for simple cubic, the example is polonium. Okay. And my dear, when we are talking about after simple cubic, if we are talking about this FCC, for FCC, the examples are gold, silver. Okay. We are having copper, aluminium, and also iron in the range of 910 to 1450 degrees Celsius. Iron is the only element of the periodic table which is going to show 4 transformation. Means it changes the crystal structure many times. First of all, it is changing from liquid to BCC structure. When it first solidify at 1550 or 1535 or 39 degrees Celsius, for the first time after solidification it shows BCC structure. Then my dear, at 1450 degrees Celsius it converts to FCC. Then my dear, once again at 910 degrees Celsius it becomes BCC. Then my dear, once again around 727 degrees Celsius it becomes BCC magnetic. So that is why if you have iron at room temperature, that will be showing you magnetic characteristic that may get stick to the magnet. But after that temperature, it will not be showing the magnetic characteristics. So guys, this is how the iron is changing its crystal structure again and again. And any material, if changes the crystal structure so many times with temperature and pressure, such an element is given the name of allotropic element. So that is why iron is said to be allotropic iron. Then my dear, for face centered cubic we have already discussed. Now we will talk about HCP element. HCP elements are looks like this. In HCP element we are having a basal plane at top. What is basal plane? This is having 6 corner atoms like this and 1 face center atom. And guys, similarly you will be having second basal plane here. Second basal plane here like this. Second basal plane here like this. It will also be having 6 corner atoms and 1 face center atom. And guys, there are 3 atoms which will be present in the body center, okay, and they will be on alternate face. Like if one atom is present on this face, then second atom will be present on this face and third atom will be present on this face. And when I am saying they are body center atom, they are not going to have center at this plane. They will be just touching. So one atom here, second here, third here. They will be touching these 3 faces. And if you see guys, this is basal plane 1, this is basal plane 2. The difference and the gap between these 2 basal plane is C and A is the lattice parameter. C is generally given as 1.58 to 1.71 A. Okay, so you can see C is more than A. Why 1.58 to 1.71? Why it is in a range? Depending on different material. As I said, based on different atomic radius, they will be showing different structures. So that is the difference. But anyhow, you can say C is much more than A. And you know, generally, if thus atoms are having electrons and nucleus, 2 atoms have positively charged nucleus, negatively charged electrons. Positive charge nucleus are having some kind of repulsions. Negative charge electrons also have some kind of repulsions. But my dear, positive charge and negative charge, they will have attraction. Similar charges repel each other, opposite charges attract each other. So that is why between any 2 atoms there are a lot of attractive and repulsive forces are present. So my dear, it have been seen or observed when 2 atoms are going away from each other, attraction increases. When 2 atoms are coming close to each other, repulsion increases. So there is a distance between 2 atoms at which attraction and repulsion are becoming almost equal. So that difference or that distance is said to be the bond length. At bond length, atoms always want to be present. So my dear, if the distance here C is more than A, so the distance between this atom is going to be more than the bond length for sure. And if that is the case, because if bond length let us say is A, then this gap is more. So my dear, if the atoms are away from each other or closer to each other, then you will be having some kind of instability. Like if you are in a job and you are feeling unstable, you will be always ready for a shift. If you get a good offer, you will just jump to the second company. The same thing, my dear, is happening. Here these atoms are at far away distance. They are feeling unstable because they are not at bond length distance. They will always be ready to move. So if some external force will be provided, it will be very easy to move the basal planes or atoms along the basal planes. That is why HCP elements are going to be used as solid lubricants. Okay. Similarly, my dear, if we are talking about the BCC materials, then if we have already seen the HCP materials for HCP, yes, graphite, molybdenum sulfide, zinc, cadmium, they are some materials which shows HCP structure. Next, we are talking about the BCC material. For BCC, when I talk about BCC materials, example is tungsten, chromium, vanadium and iron except 910 to 1450 degrees Celsius. So my dear, I would like to add one point here that BCC elements are having a bad habits, that they, whenever they see the carbon present nearby, they make the carbides. Metals have a bad habit, when they see oxygen all around, they make metal oxides. So my dear, when these BCC elements will be making tungsten carbide, vanadium carbide, chromium carbide. So my dear, because of this carbide formation, which are very, very hard phases, they will not allow the slip to move. That is why whenever these elements are added, they are going to increase the strength of material for sure. Other than that, as their hardnesses are more, they will increase the hardness of the structure also. Other than that, my dear, they are also said to be grain size refiner. Because they are hard phases, they will not even allow the solidification front to move. So that is why, my dear, when we are talking about grain size refiners, that is why, my dear, they are not allowing the grain size to increase much. I would be telling you, like if you are having a molten metal like this, then my dear, whenever the solidification start like this, if somewhere tungsten carbide is present, that will not allow this to move further. That will stop it here. So my dear, because of that, this grain will not be able to move further. That is why the grain will get shrink. So that is why when grain will shrink, its size will reduce. I will be saying it is to be grain size refiners. And guys, even tungsten carbide increases the wear strength of the material. Vanadium carbide increases the fatigue strength of the material. Chromium carbide increases the corrosion resistance. So this is how it is going to help us. Okay. So this is about FCC, HCP, BCC. Now we are talking about the average number of atoms in a unit cell. So my dear, average number of atoms in a unit cell is given as corner atoms /8 plus face center atom /2 plus body center atom /1. This is the formula for cubic structure. This is the formula for cubic structure. This is the formula for cubic structure. Guys, please tell me, are you getting it or not? I am going in a manner so that everything will be revised in a quick manner. Material science is a big subject. So if I am going for each and everything explanation, it may take a long time. That is why I am going quickly like this, and I am covering every point which can be there in the exam. So if you are just revising with this session, you will get good marks for sure. Okay, that is for sure. So Maniket, Lakshay, Sai, Krishna, are you getting it or not? Sarvanti, please tell me. Pinky, Tarun, Ganesh. Yes. So my dear, when we are going to apply this formula for simple cubic, my dear, then simple cubic will give you average number of atoms to be equals to 1. When you will be applying the same formula for BCC, average number of atoms will come out to be 2. When you will apply the same formula for FCC, average number of atoms will be coming out to be 4. Similarly, my dear, if you will be going for HCP structure, hexagonal close pack structure, the formula for average number of atoms is slightly changed. It is Nc by 6 plus Nf by 1 plus Ni by Nf by 2, Ni by 1. Why this is the formula? Because my dear, in hexagonal, in hexagonal, we are having one atom to be shared, one corner atom to be shared by 6 unit cell. That is why here NC by 6, NF by 2, Ni by 1. And for HCP structure, when you will be finding out the average number of atoms, you already know we are having 12 corner atoms. Thanks guys. Then we are going to have a 2 face center atom, and then we are going to have 3 body center atom. So it will be 2, 1, 3. It is coming out to be 6. So my dear, these are the average number of atoms calculation. You will be directly asked the question from that. Okay. So you will be directly asked that the average number of atom in this structure is. That kind of questions comes in ESE. So guys, what is the significance of this calculation? Strength. More the number of atoms, more will be the bonds. For more bonds, more will be the energy required. So that is why I will say strength is a property which depends upon the average number of atoms. So guys, that is why as FCC is having more number of average atoms, it is said to have more strength. Okay, FCC are found to be more ductile and having more strength. BCC are said to be more hard and brittle. HCP is slightly less ductile, slightly less strength than FCC. The reason for that is the basal plane gap, because of which movement was easy, and that is the reason. Even though HCP is having more number of atom, but strength of it is lesser than the FCC elements. Okay, moving further guys, average number of atoms we have seen. Now we are coming about the coordination number. So my dear, when we are talking about coordination number, this is telling you that one atom is connected to how many atoms. In space, lines are not available. So if you take any atom, it will be having connection with a number of atom. Okay, and that number of atom is said to be coordination number. Actually, it is nothing but it is telling you about the equidistant neighboring atoms. Okay, equidistant neighboring atoms. This is the definition of coordination number. When we are living in a street, how many people who are living nearby, we call all of them as neighbors. But in coordination number, only those neighbors are counted which are in direct contact. So guys, based on that, when we find out the coordination number for simple cubic, it comes out to be 6. For body centered cubic, it comes out to be 8. For face centered cubic, it comes out to be 12. For HCP, it comes out to be 12. Now my dear, more neighbor will help us to retain elasticity, because if more neighbor means more helping hand. If you will be facing difficulty in your life, then neighbors will try to help you because they are your friends. Okay, they will try to help you. More helping hands, you will be once again coming back to the original position. That property is nothing but elasticity. If I apply the load, after removal of load, body is coming back to original state. The reason for that is elasticity. And the elasticity is something which depends upon coordination number. Because my dear, if you are going to apply some forces, if one atom is moving away from its position, then the neighboring atoms will be facing that this atom is going away. When the atoms are going away, attraction increases. Because of that attraction, after removal of load, atom will come back to the original position. So my dear, elasticity and rigidity, these are the types of property which are depending upon the coordination number. We can go for the calculation. Even I have taken one marathon in the first week of February, not first week of February, last week of January. If you will see that marathon, I have derived them also. But dear, today I feel it will be wastage of time because you need to study complete material science, ECEE part also. So that is why I am just going for the point to point things which will directly be coming in exam. That is why marathons are scheduled. So moving further guys. After coordination number, A to R ratio we have already seen. Now we are coming to a very, very important calculation, that is APF. Let me go to the APF slide. Yes, APF slide I am going. You can see how the atoms looks like. This is the real way how atoms looks like. Okay. This is simple cubic. This is body center. This is face center. So in reality they looks like this. We are showing them like this only to make our calculations easier. Nothing more than that. Very good, Pogati. So guys, now you can see here coordination number I have shown. This atom is in contact with 6 atom. That is why for simple cubic coordination number is 6. Okay, you can see this corner atom, all corner atoms. So this is how we can show. Okay, so moving to the APF, that is very, very important number. Atomic packing factor. It is also said to be atomic packing fraction. My dear, this is that number which tells us actually that how much part of a unit cell is filled with the atoms. Because you know, when atoms are trying to fill, you can see here, when atoms are trying to fill, you will be having some extra voidage part. Like this part, we don't have anything. This thing is said to be void. And such type of many voids are going to be there. Okay, and in different atoms, different unit cell, you will be having different voidage percentage. So atomic, sir, I am going to appear for first time ESC. Wanted to ask the we get calculator. No dear, in prelims paper calculators are not allowed. Calculators will be allowed in conventional paper only. Okay, they will be allowed in conventional paper only. So what is atomic packing fraction or atomic packing factor? That is denoted by APF. This will tell you that how much part of the unit cell is filled with the atoms. Rest part is going to be the void. Okay, so let us try to see the definition. APF is defined as volume occupied by average number of atoms to the volume of unit cell. So average number of atom in a unit cell. Why we are using average number of atom? Because whenever we are making any atom, that atom is not completely present in the unit cell. That is having only some particular part in the unit cell. That is why we find out the average number of atoms. So average number of atoms is the exact atomic space which is present in the unit cell. As we are assuming the atom to be a sphere, this is the volume of sphere. For cubic unit cell, A cube is going to be the volume of unit cell. So my dear, this is how you can find out the atomic packing fraction or atomic packing factor. And if you calculate it, for BCC it comes out to be 0.68, for FCC it comes out to be 0.74, for HCP it comes out to be 0.74. For that, what I have done, I have used A to R relation for everything. By using this relation, I will be getting everything in R. R will get cancel out, I will get these ratios. Now what it tells actually. So my dear, if BCC have 0.68 APF, it means 32% is free. Here 26% is free. Here also 26% is free. So in that free space, we can put some extra atoms, some extra material, some foreign elements. Foreign means different elements. That is said to be alloying element. So we can add the alloying element in this space. So my dear, the possibility of alloying element is more in BCC because here more gap is there. Arey bhai, more gap, more guest. Okay. So alloying elements are nothing but the guest. Whenever guest comes, they are not the part of our home. They are said to be impurity or alloying element. So my dear, otherwise don't use that word in the home, that if some guest comes, don't say that impurity aayi hai, impurity aayi hai. Okay, so impurity is used in metals, in material science. Don't use them in the regular life. Otherwise no guest will come to your home. Okay. So guys, when we are talking about these alloying elements, the more possibility is there where more gap is there. So that is why in BCC, it is having more possibility of effect of alloying element. But my dear, I would like to say one more thing. If atom is there, whenever you are going to apply the forces, whenever crack is coming, that crack is resisted by the atoms, not by the empty space. Okay. So crack is going to be resisted by atoms. So here more atoms, more resistance. Less atoms, less resistance. That is why when crack comes, BCC elements are going to fracture without much plastic deformations. Without much plastic deformation. Like glass, if you are going to just apply the forces onto the glass, it will crack soon. If the same force you will be applying on the steel glass, it will not be cracking like that. Why? Because that is FCC and that is going to be BCC. And I would like to say it will fracture without much plastic deformation. And my dear, when we are talking about them, they will be showing a lot of plastic deformation. Plastic deformation means they will be showing ductile behavior, it will be showing brittle behavior. That is why BCC is found to be brittle and FCC and HCP are found to be ductile materials. I feel you got all the explanation nicely. I am not saying directly that this material is of this type. I am telling you why it is of this type. So that kind of explanation you will not get at all the platforms. So I feel you got it. What is APF? Okay. So now we are moving to the allotropy. I already explained what is allotropy, my dear. If any element is showing different crystal structures at different temperature and pressure, different crystal structure at different temperature and pressure, that property is said to be allotropy. And as iron shows this property, that is why iron is said to be allotropic iron. That is why iron is said to be the allotropic iron. Okay? Are you getting it? Yes. Yes, Pagati. So moving further, guys. Now we are going for the density calculation. And you may get numerical from this in ESE 2023. You may get numerical this year from this. That is volume density. So it is defined as the ratio of weight of average number of atoms per unit volume. Its unit is gram per centimeter cube. How we will define it? My dear, volume density is defined as, first of all, average number of atoms. Average number of atoms. Okay. Then, my dear, you will be having the atomic weight. I am telling you average number of atoms are atoms per unit cell. Okay. I am writing the units so that you get how the units are coming. Atomic weight is given as gram per mole. This is the weight of 1 mole of atoms. Divided by, we will be having the Avogadro number, that is 6.023 into 10 to the power 23. This is atoms per mole. Atoms per mole. And then you will be having volume, that is A cube, or I will directly write volume of unit cell, and that is given as centimeter cube. So if you will see, mole will cancel here. Okay, atoms will cancel here. Okay, this is centimeter cube per unit cell. Unit cell will cancel here. You will be getting the units to be gram per centimeter cube. You may get this calculation. Yes, Arun Kumar Yadav, good morning. बहुत late हो गए आज आप. Okay, so this is going to be volume density. कोई बात नहीं, जो भी हम पढ़ रहे हैं वो आप इजीली समझ पाएंगे आगे भी. Okay, is it clear guys for everyone? सभी लोग समझ पा रहे हैं? बताइए. Don't worry, only this chapter is time taking, other chapters are small only. Is it clear? Okay. Okay, let's move further. बहुत बढ़िया. Ethics, okay, ethics पढ़ रहे थे, बहुत बढ़िया. चलिए, moving further. Next is the planar density. So my dear, planar density is rho p, and how we are defining it? It is defined as the average number of atoms. Average number of atoms whose planes are intercepted. Planes are intercepted. Whose planes are, average number of atoms whose planes are intercepted, okay, by the atoms, divided by the area of the plane. What do you mean by that? It means we will be finding out average number of atoms, but which atoms will be considered? Whose centers are lying on the planes. So only those atoms will be considered whose centers are lying on the plane. And my dear, you will be dividing it by the area of the plane. So I would like to say, if I will be making a unit cell in front of you like this, then my dear, the point is, for every plane we have different area. I am telling you how. I am telling you how. If I am making these three axes, if I am saying that this is the plane, then for this plane you will be saying the area is a square. If I make some another plane like this, then you know this side is root 2a. So the area of this green plane is root 2a square. Similarly, if I am going to make a third plane like this, so for this blue plane, the area is going to be root 3 by 2a square. So the point is, when we have different planes, we have different areas. So area will be changing with the plane. Even the average number of atoms will be different at different planes. So planar density is going to be different at different planes. But we have seen that in general we have three types of plane. One plane for which area is a square, other planes for which area is root 2a square, other planes for which the area is root 3 by 2a square. And when we see these three types of planes, we are having same density for all those planes whose area is a square. Same density for all those planes whose area is this, same density for those whose area is this. So the point is, if we identify the type of plane, we can directly answer about the density, because in a unit cell there are a number of planes possible. Because if you see, this plane is having area a square, this is having 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 a square, this is having, so there are many planes which are having the area of a square. So all the times if I just identify the plane, then I can directly tell what will be the density. It is like in the school, whenever we get the admission, we are getting some kind of roll number, because all the person cannot remember, like principal cannot remember the name of each and every student of each and every class, each and every section. So what they do, they give a roll number. Like they give, if you are in the 10th standard or 9th standard, they will be writing 9th standard. Okay, let us say you are the 12th student in the class, 12th. Let us say you are in batch number D. Let us say you are from 2022 batch. So they will be giving you a roll number. And by looking at that, principal will be getting information about you. Okay, 9th class, 12th student, D batch, 2022 admissions year. So when by this roll number, teacher or principal will identify you, and now after identification he can check your all the records, how many marks you get, yes or no. So guys, that is how these numbers are given. So here also, if we give some roll number to every plane, then just by looking at the roll number, I will be getting the planar density. So my dear, that is why we requiring some kind of numbers to be allotted. Like in school, we have followed this roll number. So guys, Miller have come up with such a number which were given the name of Miller indices of planes. So Miller have defined those kind of planes by which we can give identification to a plane. So Miller have defined that how we will be giving a number to a plane. He said the numbers will be rationalized reciprocals of intercept of a plane on the crystallographic axis. What do you mean by that? Let us say I am having these three crystallographic axes. On these three crystallographic axes, let us say I am having a unit cell like this. I am giving the name A, B, C, D, E, F, G, H. So let us say we are talking about the plane ABCD. If you see the ABCD where it cuts X, Y and Z axis, they are the fractional intercept. If you see this ABCD, you know the side is A. So if you talk about this plane is not cutting the x-axis, it is parallel to x-axis. So if two things are parallel, they never cuts or they meets at infinity. So if you ask me what is the intercept, what is the x-intercept of ABCD plane, I will say it is infinity, because they are going to meet at infinity. Similarly, this plane is parallel to the y-axis. And I feel you know whenever we give x, y, z name, it must follow right hand thumb rule. If you keep the fingers towards x, rotate them towards y, z will give you the direction of thumb. Thumb will give you the direction of z. So my dear, if I am saying ABCD plane, it is not cutting the x-axis parallel to x-axis. It is parallel to y-axis. So here intercept is also infinity. And my dear, here it is cutting at A. A is having a value of 1.271365 angstrom. Every time I don't want to write this, I got this value from X-ray diffraction experiment. So rather than writing this again and again, I will say that I will be taking it approximately 1. So I would like to say that reciprocal of infinity is 1 by infinity. Reciprocal of infinity is 1 by infinity, and z-intercept we have kept 1. So 1 by 1. You will be having 0, 0, 1. So my dear, we get to know that 0, 0, 1 is already rationalized. So this is the Miller indices of plane. So my dear, if any Miller indices, you will get single time 1 and 2 times 0. There are 3 index number. 1, this is x, y, z. So if you get 2 zeros and single 1, it may be 0, 0, 1. And it is represented without a separating comma. If you have 0, 1, 0. If you have 1, 1, 0. Sorry, 1, 0, 0. For all these types of plane, the area is going to be a square and their density will also be same. We will calculate the density also. But that is the thumb rule. Okay. Similarly, my dear, if I am going to take some other plane, like this, this is x, y, z. This time I am talking about a plane which is like this. This is E, F, G, H. If you see E, F, G, H, it is cutting on x-axis at A. So I will say x-intercept is 1. X-intercept is 1. On y-axis it is going parallel, infinity. Z-axis it is cutting at A, 1. So I will say 1 by 1, 1 by infinity, 1 by 1. It will be 1, 0, 1. So if you have 2 times 1 or 1 times 0, all these plane will be having the area to be root 2a square and density for all of them will be same. हाँ डियर, A नहीं लेते, हम 1 ले लेते हैं क्योंकि बार बार A लिखना is not good. A is number 1.27, बार बार क्यों लिखना? So for that purpose we are taking it as A only. Rahul, Arun, Maniket, Sarvanti, Anirban, everybody getting it or not? Yes, Rishikesh, Diksha, Pogati, Ajit, everybody is getting it. Please tell me that. So this is how we will define the Miller indices. Now we are moving to the third plane, my dear. Third plane. X, Y and Z. And this time the plane I am going to select is this one. This one. This is A, B, C, let us say. If you see this plane, this is cutting x-axis at 1, y-axis at 1, z-axis at 1. Everywhere intercept are 1, 1 and 1. Reciprocal of 1 by 1, 1 by 1, 1 by 1. They are already rationalized 1, 1, 1. So my dear, if you have a plane with this number, the area is root 3 by 2a square and it is going to be having the same density all the time. बहुत बढ़िया पंकज, wonderful dear. Rishikesh, बहुत बढ़िया. Wonderful guys. So this is how we will be getting this. Okay, this is how we will be getting this. So guys, moving further, I feel we have seen. Now we are going to see the characteristics of Miller indices of planes. So when we are talking about the characteristics of Miller indices of plane, the very first characteristic is when a plane is parallel to an axis, its Miller indices is 0 on that axis. You can check it. This plane EFGH was parallel to y-axis, Miller index is 0 at that. Okay, that is the first point. Second is two parallel planes have same Miller indices. Two parallel planes have same Miller indices. Same means they will be having the same number of zeros and 1. They will be having the same number of zeros and 1. So my dear, next is the angle between two planes is defined as this. And those two planes are H1, K1, L1, H2, K2, L2. Okay, this is the angle. And if this summation of the product of these is going to be 0, then theta is going to be 90 degree. Is it clear? So these are the important points, guys, from which direct questions can come. Okay. Yes, Pankaj, is it clear or not? Please tell me that. And Pankaj, after the class, you can talk to me. I feel you have asked some 2 to 3 things. I have done that thing. I'm thinking that whether you know that or not. So you can contact with me after the class. Okay, today. Moving further. Now, my dear, if you want to find out the distance between two planes, then the formula to find out distance between two planes or distance between origin and a plane. So we are having a plane H, K and L. You want to find out the distance of this from the origin. Then the formula is D is equals to A divided by square root of H ka square, K ka square, L ka square. So my dear, I would like to say that if H, K, L, you see, they are coming in denominator. So if these numbers are going to be bigger, then distance is going to be smaller. It means if for a plane we have bigger index number, it means that plane is near to the origin. Like if we have index number of 100 and if we have index number of 300, then my dear, this will be near to origin. This will be near to origin. Are you getting it or not? So this is how we can show all these wonderful characteristics from which you can get the direct questions. Okay, is it clear for everyone? Everybody is getting? Yes. So these are the formulas. Now we are moving, my dear, to the next thing. These things I feel we have seen A to R ratio and everything. Why they are coming again and again. Okay, for planes we have seen. Now, my dear, we are moving to the, just wait. Okay, now we are going for the planar density calculations. So guys, we have already identified the planes now. Now it's time to calculate the density. And after calculating the density, my dear, we will be going for the Miller indices of directions. We will see the density which is said to be linear density. After going for all these density calculation, crystal structure will be over. Then within 20-25 minutes, we will complete crystal defect. Similarly, 20 minutes for strengthening mechanism, 1 hour for phase diagram and heat treatment. Okay. And we will also discuss mechanical properties. Okay. Yes. Moving further. So when we are talking about the planar density calculations, first of all, we will be talking for body centered cubic, BCC elements. So when we are going to calculate the planar density calculation for BCC element, then my dear, I am going to make a unit cell. Okay. And for that unit cell, we will be taking 3 types of plane. 3 types of plane. First type of plane is ABCD type. ABCD. So if we are going to see the ABCD plane, then you can see, my dear, this ABCD plane is having a Miller index number of, it is parallel to X and Y axis. It is parallel to X and Y axis. So its number is 0, 0, 1. You know, if it is parallel to XY, their index number will be 0 there. So my dear, if you see this plane, when we are talking about FCC or BCC, for BCC only, you will be having the corner atoms. And for planar density consideration, we are assuming the atom is not to be sphere but a circle. For a circle, 1/4 of the atom is coming inside because 90 degree is the angle made. So 90, 360 का 1/4 है. So that is why when you will calculate the average number of atoms for BCC, because body center atom will not be having center on ABCD. So my dear, that is why the average number of atom is going to be 1/4 into 4. It is going to be 1. So planar density will be coming out to be 1 upon A square. Please tell me you got it or not. Please tell me you got it or not. Please tell me you got it or not. This is for ABCD plane. Now we will be talking about the same for FCC. The same for FCC. In case of FCC for this plane, you will be having no doubt 4 corner atoms, but also one face center atom. And as atom is circle, so this entire atom is coming onto this plane because its center will lie on this plane. So this time average number of atom will be coming out to be 1/4 into 4 plus 1. It will be 2. So density will be coming out to be 2/A square. So this is the planar density for, and they will be directly asked in the paper, you have to answer it. I feel everybody is getting it. Please tell me, is it clear or not? Then we will be moving further. Is it clear for everyone, guys? Shall we move on now? Shall we move on now? बहुत बढ़िया. Yes. Okay, so guys, we are moving further now. So moving further, for the second type of plane, I will be once again making a unit cell. So guys, these calculations I am showing you to give you some confidence. Otherwise you will be saying, sir is saying everything to mug up. Okay, but what we will do 1 week before exam, the same thing. This time this is the plane. Let us say A. Okay, so this time the plane is AFGD. And this plane is, it is parallel to which axis? Y axis. 1, 0, 1. Yes. Great. So when we are talking about this plane 1, 0, 1, then my dear, how we will find out the density for this? This time, I will be making this plane once again like this. When it is a BCC structure, for BCC, this time you know it is a diagonal plane on which the center of body center atom will lie. So you will be having a body center atom completely because it is a circle now, and once again the corner atoms. So guys, this time 1/4, 1/4, 1/4, 1/4 and 1. So average number of atom will be coming out to be 1/4 into 4 plus 1. It is 2. So planar density will be coming out to be 2/√2A square. This is for BCC. Now we will go for FCC. For FCC, you will be having the corner atoms and the face center atom which will be present on this face. It will be half present here, half above this. Similarly, half present this, half below this. So I will be making face center atom also like this. Half on this plane, half on other plane. So once again you will be having the average number of atoms to be 1/4 into 4 plus 1/2 into 2. It is coming out to be 2 and density will be coming out to be 2/√2A square. Everybody got it or not? Please tell me that. Great Arun, thanks for that. And I feel आपको सब कुछ समझ में आया आज. Is it clear for everyone? Yes, Rushikesh, Pankaj. बहुत बढ़िया. Great. Moving further, my dear. Now, my dear, we will see the third type of plane. Which is having Miller index number as 111. So guys, this time the Miller index number we will be considering as 111. This is the plane. So 1, 1 and 1. So it is EGD, let us say. EGD 1, 1, 1. So guys, when you will see BCC or FCC, first of all let us see BCC. So when you will be looking at BCC, here there is a confusion that body center atom will lie on this or not. For that, first of all I will be showing you X and Y axis. If you see X and Y axis, here there will be a corner atom. And if you will be having a body center atom, the distance of the center of body center atom to the origin is going to be 2r. Now my dear, we can find out the distance of this plane from the origin with the formula of interplanar distance, that is a by square root of h ka square plus k ka square plus l ka square. It is a by root 3. A for BCC is 4r by root 3. So 4r by root 3 when you will do, it will be coming out to be 1.33r. You can see 1.33r is less than 2r. It means the plane will be passing before this center of atom. And if the center of the atom will not be present on the plane, then that atom is not counted. So for BCC we will be having only and only corner atoms. And this is going to be an equilateral triangle because all the sides are root 2a. So as all the sides are root 2a, so my dear, this angle 60, this angle 60, this angle 60, which is 1/6 part of a circle. So I would be saying, if you want to find out the average number of atom, it is 1/6 of 3 atoms. The atom is going to be 1/2 and density will be coming out to be 1/2 root 3/2 1 by root 3 a square. This is the planar density. And if you see the FCC, you know, they are the diagonals of all the face. So corner atoms will be there as well as face center atom will also be there. But all face center will be half in the plane and all corner will be 1/6. So here average number of atom will be 1/6 into 3 plus 1/2 into 3. So you will be having 1/2 plus 3/2. It will be coming out to be 2. And planar density will be coming out to be 2 by what is the area? Root 3/2 a square. So it is 4 by root 3 a square. Everybody got it or not? We have done all the density calculations. And guys, if you want, you can remember also. If you want, you can find out also, because I have shown you with the proper calculation each and everything. Please tell me guys, are you getting it or not? Then we will be moving further. Please tell me guys, are you getting it or more or not? Then we will move further. Is it clear for everyone? Yes, tell me guys. This is the density calculation over. Now my dear, if I show you all the density calculation in one table, if I show you all the density calculation on one table, then my dear, we have found out it for 3 types of planes. We have found out for plane 0, 0, 1, for 1, 0, 1 and for 1, 1, 1. For 1, 1, 1 in BCC it is 1 by root 3 a square. It is 4 by root 3 a square. For this it will be 2 by root 2 a square. It is 2 by root 2 a square. And when we have calculated for 0, 0, 1, it was 1 by a square. It was 2 by a square. So my dear, you know root 3 is 1.732, which is less than 2. So that is why, as root 3 is less than 2, this 4 by root 3 will be more than 2. So the point is, what I want to say here, I want to say that out of these 3, this value is the maximum. And out of these 3, this value is the maximum. You may be thinking, sir, why you are interested in the maximum value? I would like to say, my dear, for BCC 101 or 110 or 011, and for FCC it is 111. These are the planes of highest density. So my dear, on these plane, if density is more, the atoms will be closely specified. They will be closely spaced to each other. Arey bhai, if in the same space I am having 4 atoms, but in the same space I am having 40 atoms, obviously the atoms will be closer to each other. If the same page I write 100 words, in the same page I write 120 words, in case of 120 words, words will be closer to each other. So the point is here, the densities are maximum, atoms will be closer. If atom will be closer, instability will be there. They will try to go far away from each other, because when atoms comes closer, repulsion increases. So because of that, my dear, there will be the maximum instability. And where instability is there, atoms try to move. So here atom will try to move. And if they will try to move, they are unstable, it is easier for us to give the motion from there. So my dear, that is why the slip will occur across these planes, and that is why these planes are known as slip planes. That is why these planes are said to be the slip planes. So slip planes are the planes along which the motion is easier for the atoms. Yes, Payash, good morning dear. So shall we move on, guys? Is it clear for everyone? So slip planes are the planes at which slip is going to be easier. What is slip? Slip is movement of dislocation. What is dislocation? Dislocation is a group of atoms. Like there are 4 friends who left their home and they are going. They are dislocated from their homes. So I will call that group as a dislocation and their movement as slip. Okay, so this is how the things are going to happen, my dear. Moving further now to the linear density calculation. Now we will talk about the linear density calculation. Okay, now we will talk about the linear density calculation. So planar we have completed. Now we will talk about the linear density calculation. So guys, when we are talking about linear density calculation, denoted by rho L, it is the average number of atoms whose centers are intercepted by vector divided by length of the vector. So guys, that is said to be the linear density. Thanks guys for your wonderful response. Moving further, my dear, once again the length of vector and average number of atoms are not same along all the vectors. You may be saying, sir, what is vector now? We know what is plane, but what is vector now? So my dear, if I will be having a unit cell like this, then my dear, you can take a vector like this. You can take a vector like this. I am saying this is O, this is A, this is B, this is C. If you see OA vector, the length is A. If you see OB vector, the length is root 2A. If you see OC vector, the length is root 3A. So you can see the length is different for different vectors. So if length is different for different vectors, it means, my dear, the density will also be different at different vectors. So my dear, if that kind of difference is there, once again the same thing, I need to identify the planes, because we will be having 3 types of plane. One with length A, other with length root 2A, other with length root 3A. So there are only 3 types of plane, one with length A, other with length root 2A, other with length root 3A. So my dear, there are so many such vectors. Like if I ask you what is this, you will say, sir, A. What is this? Root 2a. What is this? Root 3a. So there are many vectors which have length a, which have length root 2a, which have length root 3a. So guys, we just need to identify. There are many students who are in 9th class. How I will be identifying? By their roll numbers. This time once again Miller came. He said, I will be providing you the roll number formula for this also. And for them they have given Miller indices of direction. They are quite easier than the planes. They are very easy to identify. I am telling you how we will see Miller indices of directions. We have seen Miller indices of planes. Now we will see the Miller indices of direction. They are very simple. They are rationalized component of a given direction vector. What do you mean by that? What do you mean by that? What do you mean by that? If you have a unit cell like this, then my dear, you just need to see where is the vector. If someone says that this is the vector x, y, z, what you need to do is, you will be saying if this is the vector, this is the tail, this is the head. You will write that vector. And my dear, assume this to be origin. Assume this to be origin, write down the coordinate of this. You know, for writing this vector, you have went one step here, other step here. So this is x, this is z. So this will be 0, 0. Y, you have not gone anywhere. Sorry, it is going to be 1, 0 and -1. This is how you move. You moved 1 in x direction, 0 in y direction and -1 in z direction. So my dear, because this is origin, so 1, 0, -1 is already rationalized. Write that in the body bracket, 1, 0, -1. -1 will be represented at 1 bar. And it will be treated as 1 only. 1 bar will be treated as 1 only. -1 will be treated as 1 only. So this is 1, 0, 1 bar. So if you see this, there are 2 1s and 1 0. There are 2 1s and 1 zeros. So my dear, if you are having this vector, this is already rationalized, this is the Miller indices. Similarly, if you want to write for a vector, I am saying as this one. Name this as O, name this as B. So if this is origin, what will be the coordinate of this? Coordinate of this will be, you moved into x, you moved into z, it is 1, 0, 1. So I will be writing the Miller index to be 1, 0, 1. Just without a separating comma. So my dear, if you get any vector which is having 2, 0 and single 1, 2, 0 and single 1, 2, 0 and single 1, for them the length is going to be A. Length is going to be A. If you are going to have any vector with 2 times of 1, 1 times of 0, then my dear, for them the length is root 2A. This is root 2a and this is root 3a. How root 3a? Root 2a and a. Apply the Pythagoras. It will be root 3a. So if you have a vector with 1, 1, 1, the length is root 3a. Guys, please tell me you understood this, what I just told, then I will move further. You understood the Miller index of direction, or you want me to calculate 1 to 2 more? Just tell me, guys, because without you tell, I cannot know that. In online, your expressions I cannot see, I can see only your comments. So tell me, guys, everybody is clear or shall we move on? Everybody, Maniket have said yes. Pankaj, are you getting it? Rushikesh, Arun, Sarvanti, Pogati Ganesh, Manoj, okay, Payash, great, great, great. So guys, moving further. So guys, now we know how to find out Miller indices of direction. Now let us see the characteristics of them. Okay. So my dear, if you want, I can make 3 more to make you clear. This is x, this is y, this is z. Now I am making 3 vectors. One is this, other this, other this. This is A, B, C, D, O, E, F, G. So if you see vector OD, okay. So you will be writing first of all OD. If you see vector OD, It is going to be, what is the coordinate? It is x0, y0, z1. So you will write 0, 0, 1. Similarly, if you have OC, for OC you will be having, how you will write the coordinate? It is 1, 1, 1. Because x is 1, z is 1, y is 0. So you will be writing for OC 1, 0, 1. For this you will be having 1, 1, 1. So you will be writing for OB as 1, 1, 1. This is how coordinates will be defined. I feel everybody is getting it. बहुत ही बढ़िया. Wonderful guys. So moving further now. Now we will see the characteristics. Like you remember, whenever a plane was parallel to x-axis, then my dear, Miller index number for x-axis was 0. Here it is opposite. When a direction is perpendicular to an axis, Miller index on that axis is 0. If you see this, this is perpendicular to x and y. That is why for x and y, Miller index was 0. First point understood. Second is, for two parallel direction, you will be having the same Miller index, because you know, if we have this, we are assuming this to be origin. If we will be having this, you will be assuming this to be origin. So they will be having the same Miller index number. Then if you have two directions, the angle between these direction is given by this. And if this summation is going to be 0, the angle will be perpendicular or 90 degree. A direction vector and a plane having the same index, they are perpendicular. Like if you are saying there is a plane with 0, 0, 1 and there is a direction with 0, 0, 1, then they will be perpendicular to each other. They will be perpendicular to each other. So guys, they were very easy. Now let us see the density at linear directions, and after calculation of density, we will be moving to the crystal imperfection. That is small topic. Only this chapter is bigger, which takes more time. Moving further guys. Moving further. Now we will see the linear density calculation. I will try to finish that in next 5 minutes. Okay. So guys, this is going to be a unit cell. This is going to be a unit cell. X, Y, Z. So guys, now we are going to say one by one, we will be taking the different directions. First, I am taking this OA. This is OA vector, which is having the Miller index as 0, 0, 1, because they are perpendicular to x and y. If you want to find out the density calculation, whether you go for BCC, you will be having only the corner atoms. For corner atoms, if you see, the average number of atoms are coming out to be 1 by 2 into 2. It is 1. So linear density is 1 by A. And if you see for FCC, once again the same thing will come. For FCC also the linear density is 1 by A. Because face center atom will not be having center onto this. Body center atom will not be having center onto this. So both will have same density. Now I will be talking about the second vector, which I will be showing with the blue color, that is OB vector. For this you can write 0, 1, 0, 1. So I will be writing for OB vector, the Miller index is 1, 0, 1. Because it is perpendicular to y-axis. So Miller index on y-axis will be 0. So my dear, if you will be finding out for this vector, when you are talking about the BCC, then for BCC only corner atoms will be there. And you will be having the average number of atoms once again equals to 1 by 2 into 2. It is going to be 1. So density will be coming out to be 1 by root 2A. But my dear, if you will be looking at FCC this time, you will be having corner, face, center, corner. So average number of atoms will be coming out to be 1 by 2 into 2 plus 1. It is going out to be 2. And linear density is going to be 2 by root 2A. And guys, then we are going to have the third OC vector. OC vector I will be showing with a different color, let us say white color. OC vector will be having 1, 1, 1. So you will be having OC as 1, 1, 1. So when you will be having this time 1, 1, 1, even for BCC, as it is passing from the diagonal, from the center, body center atom will be coming. So average number of atoms will be coming out to be 2. 1 by 2 into 2 plus 1 is 2. And density will be coming out to be 2 by root 3a. And if you see the FCC, only corner atoms will be coming. So average number of atoms will be nothing but 1 by 2 into 2. It is 1 and density will be 1 by root 3a. So guys, everybody is okay with the calculation. Shall we move on? हाँ अरुण वो मैं बता चुका हूँ. APF is already covered. All other characteristics are already covered. Okay. So after this all calculations, I will be making a table. If you want, you can directly remember the table also. Okay. You can directly remember the table also if you want. So we have three direction. One is 0, 0, 1. Other is 1, 0, 1. Other is 1, 1, 1. For BCC, when we have seen the 0, 0, 1, it was 1 upon A. For FCC also 1 upon A. For 1, 0, 1, we have seen for BCC, it was 1 by root 2A. But here it was 2 by root 2A. For 111, it was 2 by root 3A. It was 1 by root 3A. So my dear, here if you will see, for BCC, 1, 1, 1. For FCC, it is 1, 0, 1. Obviously, here will be 0, 1, 1. Here will be 1, 1, 0. So these are the planes. Not planes, directions. These are the directions with highest density. If I am saying highest density, what do you mean by that? Atoms will be closely fitted in the space. So if atoms will be closely fitted or closely spaced, they will be near to each other. Once again, instability will come. It will be easier for the atoms to move along such directions. That is why, my dear, slip will be easy along these directions. That's why these directions are said to be slip directions. Slip directions. So my dear, closely packed planes were slip planes. Closely packed directions are slip directions. Slip is nothing but the movement of dislocation. Dislocation is nothing but the group of atoms dislocated from their position. Now my dear, what do you mean by this slip planes and slip direction? We are defining a term number of slip systems. Number of slip system is defined as the number of slip planes into number of slip directions. That is said to be the number of slip systems. And if number of slip systems are going to be more, the chances of slip is going to be more. Slip indicates plastic deformation, that is ductility of the material. So my dear, if number of slip systems are going to be more, the ductility is going to be more. So we can say FCC material and HCP material, when we compare, then the number of slip system for FCC are more than the number of slip system for HCP, and that is why FCC is said to be more ductile than HCP. This was the wonderful explanation, my dear. For this wonderful explanation, I am teaching you for last more than 1 hour, and in the class also I teach this for 2 to 3 classes, means 5 to 6 hours, to just tell you why FCC is more ductile than HCP. But as material science is having the characteristics of chemistry, even though with so much explanation, exceptions are there. When you see the number of slip system for BCC, it is not less, but found to be more than FCC. So as per the rules, yes, Suresh, I didn't get what you want to say. So my dear, if we are talking about the BCC, the number of slip system of BCC, as BCC is found to be brittle, but still when you are going to find out, when we are going to find out the number of slip system, it is found to be quite more than that of the FCC. With the rule, as per the rule, if we go for, then BCC must be more ductile than FCC. But you know, BCC is found to be brittle. So like chemistry, it is also showing the exceptions. If you remember, there was a web series Quota Factory, where students are just not happy with the inorganic chemistry because a lot of things to mug up are there. When they learn some rule, they get to know that rule is not followed by that element. So they say exceptions are more than the elements who follow the rules. So here also material science have the same nature of chemistry. So my dear, we found BCC elements to be brittle, even though they have more slip system than that of FCC. But guys, here it is not like to mug up. Here there is a reason behind that. The reason is, for atoms to move, slip direction and slip planes are required. But my dear, in case of FCC, slip plane and slip directions are going to be oriented with each other. So atoms are moving along a slip plane, then along some slip direction. So movement go on with continuity. But in BCC, if one slip direction is here, other slip plane is like this, they are randomly oriented. So for the atoms to move, they do not get the continuous path. So that is why they stuck after some time. And that is why plastic deformation is not possible to much extent. And that is the reason, even though with more number of slip systems, BCC elements are found to be brittle. But here the explanation suits good. For that, I told you all these things. So guys, if you understood this, with this crystal structure is over, now we are going to move to the second part, which is nothing but the crystal defects. Is it clear? Is it clear for everyone? So guys, do like and share the session. You can see from morning I am telling you all these things. Okay. Solve 1 to 2 questions so that you get an idea how questions are asked in the paper. This is first question. What is the volume of FCC cell in terms of atomic radius? You know, volume is given as A cube. A is given as 4R by root 3 for FCC. No, it is 2 root 2R for FCC. For BCC, it is 4R by root 3. Maniket have answered it as B. So guys, you just need to put the value of A. What is A? 2 root 2R. And you won't believe these are the types of question which comes in ESE. Okay. Pius should also say the answer is to be B. B is the right answer. Moving further, guys. What is the linear density of FCC 100 direction in terms of atomic radius? This time, let us say how many of you give the right answer. I will not give any hint this time. I will not be giving any hint this time. Try to solve it, guys. Try to solve it without a hint. Try to solve it without a hint. Yes. Try to solve it without a hint. Yes. So many of you are saying B, 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 B. Some are saying A. Let us see, check it. For FCC 100, the linear density we have calculated as 1 upon A. For FCC, A is 2 root 2R. So the answer is B. Yes or no? Very good. So B is the right answer, guys. So moving further, guys, now we will see. Actually, I have many questions. Okay. Okay. One more question. Let us see the interplanar distance in these three. So you know, interplanar distance formula is A divided by square root of H square plus K square plus L square. Try to solve it, guys. Try to solve it. You need to find out for 100, for 110, for 111. What will be the right answer? After this, we will directly enter into the next topic. Karan Gupta already have put IES, the name B, A, Maniket is saying A. Let us see what will be the answer, guys. Let us see what will be the answer. So guys, for D100, it is going to be A by 1 plus 0 plus 0. It is A. If we see D of 110, it will be A by 1 plus 1 plus 0. A by root 2. Then you will be having D of 1, 1, 1. A of 1 ka square plus 1 ka square plus 1 ka square. A by root 3. So it is going to be A is to A by root 2 is to A by root 3. So I will be multiplying with root 6. Root 6A, root 3A, root 2A. A. Answer will be A for this. Okay. Sorry, Karan, I was not aware of that. That's really great. Congratulate on that. Yes. Sorry for that. I was not aware of that, Karan. So we are happy to have you in this session. So guys, you are having a student, a person, Karan Gupta. He is already qualified engineering services in 2022 with AIR 31. So Karan, you are from which branch? That also students would like to know. Moving further, guys, to the next question. Okay, this is the APF of copper. What is the APF of copper? Okay, civil. Great, Karan. So what is the APF of copper? So those students who qualified, they are definitely inspiration for the aspirants. Yes. Great, Payesh. So Karan, even the students at second channel are also congratulating you. Okay. So what will be the answer for this? Can anybody answer? Ganesh is saying 0.74, Maniket is saying C, and yes guys, the answer is correct. Because copper is FCC. For FCC, APF is 0.74. So these are the types of questions which are generally asked. Okay, I feel there are many questions. I will be sharing this to you. You can do the questions. Okay. Fine, guys. Now come back to the class. Okay. So guys, now we will be starting the next chapter, that is structural imperfections, crystal imperfections. When I am talking about the structural imperfection or crystal imperfection, generally students are asking, sir, are we talking about if material is not crystalline? We already know that is amorphous. So in crystal defects, are we going to talk about the amorphous material? No. We need not to see amorphous material. They are not the part of the course. Then why we are talking about? So my dear, if you are a good student, out of 30 days, you are studying very nicely in 28 days, but 2 days, you are enjoying, you are doing anything crazy, like the peoples who are not even prefer to study. Those 2 days, you are just enjoying, you are just doing masti and all. You are becoming crazy, and now no one can say that you are a student who study also. So guys, then because of that behavior of 2 days, I will not say you are not a good student. So what do you mean by that? I would like to say here, guys, that if the deviations are there from 3D long range periodicity, but deviations of very short range, like 28 days you are behaving like a good student, 2 days you are doing anything, bunking the classes, doing anything nonsense, for those 2 days I will not say you are not a good student. So guys, when something shows small range deviations, we will not call it amorphous, we will call it as crystal defects. And even at room temperature, atoms, molecules and ions are keeps on vibrating even at room temperature. Because of that temperature, they have some energy. So atoms are always vibrating because of that. And because of those phononical vibrations, they will never be fixed, they will never be stationary. So because of that, we will never be getting the perfect crystalline structure. Perfect crystalline structure is possible when the atoms are stationary, which is possible at minus 273 degrees Celsius, 0 Kelvin, absolute 0, which is not achievable. So in reality, we will never be getting the perfect crystalline structure. So that is why always some defects will be present. So we need to see what are those defects. They are the short range deviation from true crystallinity. And guys, let us see one by one all the crystal defects. Crystal defects are classified in 3 to 4 categories. One is point defect, line defect, surface defects, and volume defect. Volume defect we are not going to study here because they are the part of production or manufacturing for mechanical student. Casting defect, welding defect, forming defect, forging defect, machining defect. So they will come under volume defect. Here we need to study point defect, line defect, and surface defect. Point defect are also said to be zero-dimensional defect. Line defect is also said to be one-dimensional defect. And surface defects are also said to be two-dimensional defect. It is also been seen if at one place more than one zero-dimensional defect is present, they will give result into one-dimensional defect. Similarly, if one-dimensional defects are present more than one at a place, they will result into the two-dimensional defects. So the examples of 1D defects are vacancy, self-interstitialcy, impurity, Frankel defect, Schottky defect. What are they? I'll be teaching you. This chapter is more important. In 20-25 minutes, I will try to complete this, and this is more important than first one because it is small chapter and chances of problems are more here because they are having ESE type of theory content. So my dear, in line defect, we have edge dislocation and screw dislocations. In surface defect, we have grain boundaries, low angle tilt and twist boundaries. We have twin boundaries, we have stacking fault. So one by one, we will see all of them. Moving further, guys, to the first type of structural imperfection, we will see the defects here. You see the figure? It seems to be a perfect crystal. Everywhere atoms are present. I am showing them with the dots. Otherwise, atoms are always in contact like that. I already told you. So my dear, you can see here the atom is not present. So when some atom leave its position, then the position gets empty. And that empty position, which is a void, is said to be the vacancy defect. So if one atom leaves its position, that defect is said to be the vacancy. And my dear, you already know that when the atoms are closely packed like this space is said to be void. So obviously when this atom will be going away from its position, if it tries to enter into the void of some other 4 atoms, like these are the 4 atoms, this atom is leaving from here and try to enter into the void of these 4 atoms. I am showing these 4 atoms here. So this is the void space. If this atom will try to enter into this void, and let us say it enters, when it will be entering, obviously because of that these atom has to move away because the size of atom is more than void. Then if atom is leaving its position and it is present in the void, that void is named as interstitial site. Void is named as interstitial site. Interstitial site. So if this atom is leaving its position and try to enter into this interstitial site, then my dear, this defect is known as self interstitialcy. खुद ही की interstitial site में घुस जाना is self interstitialcy. I would like to say that when this atom was not present here, when you have seen this vacant position, you said this is vacancy. And when you have seen this atom to be present in between them, you will say this as self-interstitialcy. So this is vacancy, this is self-interstitialcy. Is it clear? So vacancy is leaving the position. If one atom is not present at its position is vacancy, and if it is present in the interstitial site, it is self-interstitialcy. And if both the defect are in neighborhood, we call it as Frankel defect. Please tell me guys, everybody clear about these 3 defects or not? Is it clear or not? Please tell me that. Maniket, I will try to cover complete, but there are some theory parts like polymers, ceramics. I will try to provide that PDF of that just for the revision purpose, because those are the things which you have to revise. Is it clear or not? Please tell me that. Fine. So these are the things which you need to understand, from which more questions are also coming. Great. Moving further. So guys, here is the more clear picture of what we have seen till now. You can see that this is a vacancy. Atom is not there. The same atom is going in the nearby, that is self-interstitial C. And as they are in neighborhood, they will be called as Frankel defect. Now my dear, if you are going to add an impurity atom, like we are having a iron metal lattice, and in this iron metal lattice, if we are going to add carbon, then carbon is smaller in the size, but it is not iron. So any outside item is said to be an impurity. Like if guest comes to your home, in the language of material science, we will call them impurity. In your home, 4 people are living, you, your mother, father and your brother. You are 4 people. Any 5th person, mama ji, chacha ji, tau ji, neighbor ji, all are impurities. Now impurities are of 2 types. One is dominating, other is non-dominating. Guests are also of 2 types. One is dominating, other is non-dominating. Like if your mama ji is coming, he will be considered under dominating. What is dominating? There you need to give love and respect both. Non-dominating means when your friend comes, you have to show love but no respect. So when your friend comes, you will be behaving very, you can say, normally. You may not be asking him for water, tea and all. But my dear, with your mama ji, you need to show the etiquettes. That is the difference. So here atoms gives the respect based on the sizes. Like carbon atom is smaller than iron. Iron will show no respect for carbon. No respect means when carbon will come, carbon have to enter into the void space. So when carbon is smaller atom, it will try to enter in the void space, and that is, it will be trying to, this is the void space. Carbon will try to enter into the void space. So that is why it is said to be the interstitial impurity. Interstitial because it is going to interstitial site. It is interstitial impurity. And if it is having more size than iron, like maybe some other element, magnesium and all, then they will be having bigger size. Then if they will come, iron will go to its self-interstitial site and iron will leave the position for that element, and that atom will substitute the iron. That is why it is substitutional impurity. Everybody got it or not? Please tell me that. It is said to be substitutional impurity. Yes. So guys, these are all the defects we have seen one by one. You can see here also vacancy, self-interstitial C, and now my dear, whatever we have seen the Frankel defect. If we are talking about the same thing in the ions, like we have a NaCl structure, NaCl. You know, Na have 2, 8 and 1 atom. Cl have 2, 8 and 7 atom. So guys, to complete its octet rule, you know that it want to have 8 electrons in the outermost shell. So it needs 1, and sodium have 1 extra. Sodium will give that electron here, and it will become Na plus. It will become Cl minus. But for breaking the bond, some energy is required. So this will happen only if you will increase the temperature, if you will provide some energy. So when energy is provided, temperature is increased. By getting that energy, sodium will give this electron to chlorine. Na plus will come, Cl minus will come, bonds will be broken. But both these will be present in the lattice only. So the charge neutrality is still maintained. Overall positive and negative charge is equal, but these ions will leave their positions. So as they are leaving this position, this defect is said to be Schottky defect. Please tell me everybody got it or not. Do like and share the session, guys. We are still at mechanical part. After me, Ashutosh sir will be coming for telling you electrical property, magnetic properties, Hall effect. Everything will be covered in detail. Okay, so guys, I feel I will be taking up to 12:30 or 1. After that, Ashutosh sir will be coming. Okay, so moving further, actually in this marathon, we are trying to cover all the important topics. Okay, and all the topics where student feels difficulty and they want to learn. There are something which are going to be mug up. What are those things? polymers, thermosetting, thermoplastic, you need to mug up. Okay. Then same with the nuclear material, same with the composites, ceramics. So those things you need to mug up. So there we will not be wasting time. There I will give you PDF which will tell you what to study, what not to study. At least that idea you will get. Okay. And by going with that, you will be easily cracking the questions. And those are the portion which generally students are not doing. But because you need not to score 200 out of 200. Why to go for unnecessary things? But I will say yes, it will be good for revision if you go from the PDF. That will be fine. Moving further, the reason for point defect. The first reason for point defect is the high temperature because of which the bonds are going to break. Okay. And second is if you are adding the impurity intentionally. So when you are adding the impurity intentionally, how it affect? Impurity will be going into either void or into the substitutional space. In both the cases, yes, Payesh. So in both the cases, what will happen? The atoms have to move relatively. It is like in a seat of auto, 3 people are sitting, and if 4th person will try to enter, those 3 person have to go like that, aage piche hokar. So because of that, some rearrangement will always take place. Like I have already shown you, if this atom will be entering here or this small atom will be coming here, then these atoms have to move. Because of that, the entire crystal will be getting some randomness. And because of that, it will be very difficult for the atoms to move along that. And that is why impurities increases the strength of the material, not because of their properties, but because of lattice distortion. Okay. So when PDF Maniket you will get on my Telegram channel, Mechanical by Dheeraj Sir. Mechanical by Dheeraj Sardana. Okay. So guys, this is something called as reason for the point defect, and effect is going to be the increase in the strength because of lattice distortion. Okay. Guys, moving to the edge dislocation now. Edge and screw dislocation. Let us see now the edge and screw dislocation. Now my dear, first of all let us see the edge dislocation. You can see my dear, here the atoms are not present. These 3 atoms are present, these 3 atoms are not present. So you got 3 vacancies together. I told you when more than one point defect is coming together, it gives result into the surface defect, line defect. So that line defect is said to be the edge dislocation. Here this partial group of atom is present, partial group of atom is not present. So my dear, this edge dislocation is denoted like this. And guys, in the same way, if here atoms are present, here atoms are not, then we will show the same edge dislocation like this. Is it clear? And guys, as you know, it is going to be a 3-dimensional structure. So if you have atom, you can see behind this also the atom will be there. Then this thing will be the dislocation line. And this separates this part and this part. This is the slipped part. This is the unslipped part. So this is said to be the dislocation line. Because of the absence of these atoms here, the gap between these 2 atoms is going to be more than the bond length. So they will be partially attracted towards each other. That is why their positions are shifted. And the velocity direction of these atoms is perpendicular to this line. The atoms are moving like this. So this is dislocation line, this is the motion direction. So that is why we will say that the direction of velocity is perpendicular to dislocation line. And direction of velocity is said to be the Berger vector. So I will say Berger vector is perpendicular to the dislocation line. This question is coming in the paper, that for edge dislocation, the Berger vector direction is parallel to the dislocation line, perpendicular to the dislocation line, both parallel and perpendicular. D, data insufficient. You will say perpendicular. So my dear, what is screw dislocation then? This is edge dislocation. When we are having vacancy at the bottom, it is said to be positive edge dislocation. When we have atoms at the bottom, it is said to be negative edge dislocation. And the Berger vector direction is perpendicular to dislocation line. Always remember these points. Question will be coming from that only. Then my dear, what is screw dislocation? What is screw dislocation? This is the screw dislocation. Okay, here you can see, my dear, here you can see how this is displaced like this. You can also feel with a cylinder. Like if I have a cylindrical surface and I apply some shear forces here, then this cylinder will get a shape of helix. How it will be taking a shape of helix? It will become like this. Like this. So my dear, you can see here this part is slipped part, this part is unslipped part, because cylinder was starting initially from here. So if that is the case, my dear, this is the dislocation line. Dislocation line is which separates slipped and unslipped part, and this time the movement of atoms, atomic planes takes in this direction. So you can say the direction of Berger vector this time is parallel to the dislocation line. In the edge dislocation, atoms were 1 to 2 atoms or 2 to 3 atoms were moving. In the screw dislocation, the entire atomic planes are moving. That is why screw dislocation happens at high temperature, edge dislocation happens at low temperature. So if you understood all these things, it's fine. If you do not understood this, don't worry. I am giving you all these things in one slide which will give you all the answers. This is positive edge dislocation, negative edge dislocation. This is perpendicular to dislocation line and it happens at low temperature. This is about edge dislocation. Now about screw dislocation. I will say it is happening, then velocity is parallel to dislocation line and it happens at high temperature. So if you see this slide, this will be helping you to answer any question on the line defects. Is it clear? And this is the beauty of this type of PDF. So guys, we are moving to the surface defects now. Surface defects. The very first surface defect is, my dear, grain boundaries. We are about to complete it. Okay, after surface defect, we will enter into the strengthening mechanism. Okay, and guys, when we are talking about the surface defects, for surface defects, the very first is the grain boundary defect. What is grain boundary? You can see, my dear, if this is the molten metal pool, you know that these walls are cooler and inside we have the molten metal. Obviously, molten metal will be hot and at high temperatures. And this container is having the cold walls. So, my dear, now solidification front will be starting. What is solidification front? If you take a bowl, put what example? If you take a bowl and in that bowl you put some water and you put that water into the refrigerator, then, my dear, if you will be putting that into refrigerator and you are not allowing the entire water to solidify, then what will happen? Then you take that out and if you will try to dip your finger into that, you will feel in between some water is there. From the sides, already water converted into ice. So what happens actually? Actually, from these walls, as these walls are cooler, because in refrigerator those walls of the bowl are cooler. So this walls of this container are cooler. Because of that, from here the water will be starting solidifying. Here I am talking about the molten metal. Molten metal will start solidifying. And that is said to be the solidification front. Here also similarly some solidification front will be moving. Here also some solidification front will be moving. Here also some solidification front will be moving. So guys, if that is the case, what do you mean by solidification front? Like unit cells are start solidifying in this direction. This direction in which the unit cells are forming, that we will also call it as grain orientation. Is it clear? So guys, that we will also call it as grain orientation. Okay, sorry for the disturbance once again. So this is said to be the direction of grain orientation. So my dear, similarly grain will start forming here, here and here, and after some time when they all will be reaching to the center, the entire solidification will take place. So my dear, if that is the case, if you see this entire structure when it is solidified, you will be having some grains to be formed like this. These grains are formed because of the grain orientations. Okay. So guys, is it clear for everyone now? Shall we continue? Ramesh. Okay. Telegram is Mechanical by Dheeraj Sardana. You can search it. Otherwise, I will share the link in between the session when Ashutosh sir will be taking. Okay, I will share it. So guys, when we are talking about the grain boundaries, you know that here some grain orientation was there, here some other grain orientation was there. So when this boundary will be formed, this will be having some particular grain orientation. So that is why this thing is said to be one grain. Similarly, if I show it with the different color, this is one grain. Then my dear, I can show you this is the second grain. Then my dear, I can show you this is the third grain. Then my dear, I can show you this is the fourth grain. So I have shown you 4 or 5 grain. In reality, the number of grains are quite big in number. Okay, the number of grains are quite good in number. Quite big, lakhs, thousands, crores, like that. So I have shown you that. So guys, wherever 2 grains are meeting, that is said to be grain boundary. So if this is grain 1, then this is grain boundary. This is grain boundary. This is grain boundary. So where more than 1 grains are getting meet, that is said to be grain boundary. The point is, why grain boundary is a defect? So my dear, you know that we want 3D long range periodicity of atoms. So here the unit cells were solidifying in this grain orientation, here in this grain orientation, here in this grain orientation. So within a grain you can expect the 3D long range periodicity, but at grain boundary you will feel some changes because grain orientation is different there. It is similar to the boundaries between 2 states. It is similar to the boundaries between 2 countries. Like in India, the boundary between Rajasthan and Gujarat, the boundary between Haryana and Punjab. All those cities which are at the boundary of Haryana and Punjab, you will find there the peoples of both the origins. In Haryana, generally people speak Haryanvi. In Punjab, people speak Punjabi. And if you see at the border of both the states, you will find the peoples of both the origin. So when peoples are of both the origin, both orientations are present. That is why that is called as defect. Maniket, don't worry, I will share my Telegram channel link in the comment section when Ashutosh sir will continue the session. Okay, I will do that. And even I will try to share the PDF of this session into BYJU'S exam prep channel also. Okay, is it clear for everyone? So guys, we are moving further. So do like and share the session. Because of that power cut issue, many students left, so that they once again get to know that session resumed. Okay, so guys, moving further now. So my dear, when I am saying that this is grain boundary, this is called as defect. So like in the boundaries between 2 states, you will be finding out the peoples of different orientation, different language, different culture. Similarly, I will say grain boundaries are the region of orientation mismatch. So my dear, where orientation mismatch is there, where 2 types of peoples are there, chances of fight is always there. Why chances of fight is there? Like if we are talking about the boundaries between 2 countries, India and Pakistan. Pakistan want to occupy the Kashmir, or India want to retain that and try to take POK back. This is just an example, don't take it otherwise. So the point is, that is why there is always a compressive influence, a fight kind of thing is there. Let us say we want to save our land, someone want to occupy that. Then at the border we will always be having some kind of fight. Fight means a kind of compressive influence. Compressive influence means there is a kind of instability. Instability means more energy. So I would like to say grain boundaries are the region of high energies. If there is high energy, chances of fight are more. Even if slight thing happen, there are chances that war will be there. So my dear, here also, if we are talking about a material, we have grains and grain boundaries. You already said that, sir, this is grain and this is grain boundary. Grain boundary have more energy than grain. If I am going to put some heat into that, grain boundary is already having high energy. Getting some energy, it will melt out. So grain boundary will be melting first. After that, grain will melt. What do you mean by that? Grain boundary have lower melting point temperatures. So grain boundaries have low melting point temperatures. My dear, always we say that Ghuspat happened from this country to that country. Like in the politics, you can say many things you must have listened that from Bangladesh, some peoples are entering into India, Ghuspat ho raha hai wahan se. So Ghuspat kind of thing always happens where we have grain boundary orientation mismatch. Why? Whenever I would like to give you an example, like in my BTech days, you know, everybody do that. When we are having the BTech days and let us say today we want to have some kind of party and we don't have money in our pocket, what we will do? We will try to search, is there any marriage nearby? We also have done that once or twice. So when we have seen, we just went with our, you can say vehicle, and when we went there, there was a marriage, a big marriage place was there and their marriage was going on and we entered into that. We went there, we have just enjoyed the party and come back to home. Why no one was no one was able to identify us? Because the peoples who were from the boy side, man side, they were thinking that maybe they are from the girl side. And the peoples from the girl side, they may be thinking that maybe they are from the boy side. Because of that orientation mismatch, they were unable to identify. Then I went there only once, but my friend had a habit of that. They went there again and again. And one day there was a birthday function. And when they go to birthday function, all the peoples were from the same family. They identify, you are not from us. And they caught them and they said, oh, sorry, we were going to some other marriage. Maybe we are at wrong marriage palace. So what I want to say that possibility of Ghuspat is there where orientation mismatch is there. So guys, are you getting it or not? Please tell me that with wonderful example. So guys, grain boundaries are the region of inclusions or heavy impurity concentration. So impurity also is coming where we are going to have the grain boundaries. That is why if more grain boundaries are there, chances of corrosion are more and more there. That is why in the applications of high temperatures and corrosive medium, we always try to have lesser number of grain boundaries. Because if you are working in the corrosive medium like sea water, chances of corrosion are more. Then if you have more grain boundaries, more corrosion, more rust, soon failure will happen. But on the other hand, if I am talking about temperature, you know, grain boundaries are the region of low melting point. So if temperatures are higher, grain boundary will melt out. So high temperature applications like turbine blades, we will try to have lesser number of grain boundaries. So at normal working conditions and at high temperature and corrosive mediums, things are going to be different. I will tell you why. Because whenever we are going to compare the grain with the grain boundaries, my dear, I will like to tell you that if we are going to have a material with less number of grains, on the other hand, we have a material with the more number of grains. More grains means more grain boundaries. So this is good in the case of high temperature and corrosive medium. Because there we want lesser number of grain boundaries. Even we will try to have only one grain without grain boundary, zero grain boundary or single grain material. We will try to have. Where gas turbine blades, corrosive medium ship in the sea water. And in normal working condition, this is better because more orientation mismatch means more difficulty in crossing them, because my dear, wherever you are having state to state conversion, you need to pay toll tax, because they are the high energy region. There will be some kind of security which will be taking the toll tax from you, means more force we need to apply. So it is difficult for any atom to move along the grain boundaries at lower temperature. But at high temperature, grain boundaries melt out. So at high temperature, more grain boundaries should not be there. At low temperature, more grain boundaries is a good thing. So normal working condition, room temperature, we will always try for fine grain material. In corrosive medium, in gas turbine blade, we will always try for zero grain boundary or single grain material. Please tell me you got it or not. We are entering to the third chapter after 5 minutes. Please tell me everybody got it or not. Maniket, you got it or not? Rishikesh, you got it or not? Ganesh, you got it or not? Payash, you got it or not? Because after me, Ashutosh sir is also waiting. So after, you can say around 1 p.m, Ashutosh sir will take the command. Okay. And then he will complete within 2 to 2.5 hours. Very good. Rajshri, very good. Moving to the next surface defect, that is said to be the twin boundaries. So my dear, initially we are having some perfect material like this. But when we are going to apply the shear distortion, it is getting distorted like this. It is getting distorted like this. So now after distortion, what you will get? After distortion, you will get this. Like this. So these two boundaries are said to be the twin boundaries. I am making it again. This is like this. Initially we were having the material to be like this. But when we apply the shear distortion, because of this, the material shifted to this red one. And you will feel this part and this part are mirror image about this mirror. So these two boundaries are said to be the twin boundaries. This defect happens because of shear distortion. And what is the effect of that? Effect of that is this distance between the two atoms is more than this distance. So because of this here, instability will happen, and that is why it will be easy for us to fail the material along the twin boundaries. The resistance will be lesser by the material, and material will be having lesser strength along the twin boundaries. Strength of the material will reduce. So guys, do like and share the session so that others can also join. We are about to complete the crystal imperfections. The next defect is the tilt boundaries. Tilt boundaries. So my dear, what is tilt boundaries? You can see here there is one edge dislocation, because after that this line will not continue. Similar edge dislocation will happen for this line also, because after this it is not going to continue. Similar is happening to this also, because this is not going to continue after that. So you are having more than one edge dislocation in the neighborhood. It will result into the surface defect. How it will result into the surface defect, I am telling you. You can see that because when here edge dislocation will come, the gap between this atom and this atom will be more. That is why they are tilted towards each other. The same tilt happen here. The same tilt happen here. That is why it is making some angle theta, and that is said to be the low angle tilt boundaries. So if someone asks you why this defect come, because of the presence of more than one edge dislocation in the neighborhood. Similarly, if more than one screw dislocation will be there, it will result into the twist boundaries. Okay. And guys, with this is the low angle twist boundaries. And now my dear, we are coming to the staking sequence. If you see the simple cubic structure, what is the staking sequence? Staking sequence is the sequence of atomic planes, how they looks like in the space. Like if you see the simple cubic structure in the space, in simple cubic structure you will be having a plane with these four corner atoms. The second plane is again with the four corner atoms. So my dear, if I will say that this plane with four corner atom is said to be plane A, then this plane with four corner atom is said to be plane A. So the staking sequence for this is going to be A. This is sequence, means how the planes are oriented. Similarly, my dear, if you see the HCP, this is HCP. This is a basal plane, you know that. Then you have a plane with 3 atoms. Then once again basal plane. So if this is A, this is B, this is once again A. So for HCP, the stacking sequence for HCP is A, B, A, B, A, B. So I feel you got what is stacking sequence. I am telling you stacking sequence for all right now. I am telling you stacking sequence for all right now. For simple cubic, A, 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 A. For BCC, A, B, A, B. For HCP, A, B, A, B. For FCC, A, B, C, A, B, C. And if by chance any stacking sequence is not followed and any one plane is absent, we will call it as stacking fault. Sandeep, are you getting? Ganesh, are you getting? Pankaj, Payash, are you getting? Arun, Maniket, Rajshri, are you getting everybody? So this is how the things are going to happen. Yes, Ramesh, thanks for that. Okay, moving further. So guys, with this, we have completed the chapter. Now we are moving to the strengthening mechanism, the third topic. So guys, after this, we are having small discussion on the phase diagrams. Then Ashutosh sir will come. Moving further, guys. So when we are talking about the strengthening mechanism to increase the strength of the material, there are 3 ways. The first way is grain size refinement. You already know that at normal working condition, fine grain structures are better because more grain boundary, more high energy regions, they will not allow slip to move on. So that is why we always want lesser size of grains if we are working at normal working condition, means at room temperature in non-corrosive medium. But that we have studied. For that, what we can do to get fine grain structure, we are having 2 ways. First way is we will be adding BCC element, because BCC elements are grain size refiners. Second, we will go for high cooling rate, because if cooling rate will be higher, we will be having more number of grains. So my dear, these are the 2 conditions by which we can increase the strength of the material. Second way is cold working. Cold working means if you have a rubber and you will try to extend the rubber. Now after extension, rubber will become tight. Now if you want to increase more, you need to apply more force. So when we deform a material, its strength automatically increases. That is said to be the cold working. So we are not interested in these 2 ways. Here we are interested in solid solution strengthening. Then what is solid solution strengthening? In the crystal defect, we get to know that if we are going to add impurity atom, lattice distortion happen. Because of that, the strength of material is getting increased. So we are here talking about that strengthening mechanism. That is also said to be the solid solution strengthening. Because those impurity we add intentionally to increase the strength of the material. Arun, for that also you will get the PDF, because that is also mugging up kind of things. There I will give you the properties of different alloying element. Like if you add chromium, what kind of property will increase? That you have to remember only. Okay. There I cannot help you anything. I can just give you notes. If I will be showing here, I can do that, but that is going to be wastage of time for others. Those who don't want to read that. Okay. So that is the point. There is nothing like explanation kind of thing in that. But first we will complete the explanation kind of thing. If after that time permits, then after Ashutosh sir, I will come for the polymers and all if time permits. If you will be free before my class, my paid class is also there in the evening. So if that part will be over, then I will come for, because in my PPT I have polymers, I have composite, I have ceramics, I have everything. So that PDF will be shared to you. Okay. So guys, now we are moving for strengthening mechanism. As I already told you that we are going to see what is the solid solution strengthening. So to understand the solid solution strengthening, first of all we need to know about the alloys. So guys, generally we are using 2 types of elements. One is alloys, other is composites. So if we are talking about alloys and composites, people are getting confused always. So my dear, when we are talking about alloys, always remember the must thing for alloy is it must have the metallic properties. So alloys must have metallic properties. That is why whenever two elements are added, one of them should be metal. Then only we will call it as alloys. So you can say alloys are of metals. At least one metal will be there out of 2 to 3 or 4 components. One should be metal. But when we are talking about the composites, composites can be made up of 2 non-metals also. So for composites, they may not have metallic properties. That is the difference between alloys and composites. Okay. So when we are talking about the alloys, alloys may be single phase, may be multi-phase, but composites are always multi-phase. You may be thinking, sir, now what is the phase? So have you seen the laddu? If you see the laddu, all yellow particles are there. In between, some orange particles are there. So yellow particle is different phase, orange particle is different phase. So in that laddu, if you are going to hit that laddu, you can take the orange particle separate. Yes, phase is mechanically separable. If you take the yellow particle of laddu and orange particle of laddu, they would be having different chemical compositions. But yes, they will be chemically homogeneous. This is what phase is defined as. Okay, so my dear, when we are talking about the alloys, let us move further. Alloys are classified into 2 categories. One is homogeneous alloys, other is multi-phase or heterogeneous alloys. Homogeneous alloys are single phase, heterogeneous are multi-phase. The example of single phase alloys are solid solution and compound. The example of this is made up of more than 2 solid solution or more than 2 compounds, or 1 solid solution and 1 compound can be there. That is the mixture. Now my dear, we need to majorly talk about solid solutions and compound, because we are going to enter into the field of solid solution. It is similar to, like when we started studying, we said one is crystalline, another is amorphous, then we left amorphous. We went with crystalline. Then I said one is simple cubic, BCC, FCC and HCP. I left simple cubic, I went with BCC, FCC, HCP. So I have left the things which were not required as per my course. So here also, my dear, we will be more concentrated about the solid solution. But my dear, there is the Gibbs phase rule from which the question can come. It is defined as P plus F is equals to C plus 1. So I would like to say here P plus F is equals to C plus 1. P is the number of phases, F is the degree of freedom, C is the number of component. This one indicate about the temperature, because pressure is 1 atmosphere for all material science activities. Okay, if temperature and pressure both are variable, then this 1 be replaced by 2. Then Gibbs phase rule become this. What is degree of freedom? The minimum number of variables required to define the state of a system. That is degree of freedom. Like if I am moving linearly in a line, to define my motion, only one axis is required. Similarly, if variables are changing, so based on the number of variables changing, we will be requiring 2 to 3 axes. That is our degree of freedom. So guys, now we are moving for the solid solution versus composite. From here, there are fair chances that question will come. So try to understand and try to learn carefully here. What is the difference between solid solution and compound? First of all, my dear, when we are talking about the compound and solid solution, both are alloys. So when we are talking about alloys, I already told you, they may be homogeneous, may be heterogeneous, but both solid solution and compounds are homogeneous. Then what is the difference? Example से difference बताता हूँ. Steel is an alloy, water is a compound, or Fe3C is a compound. You may be saying, sir, what is the difference then? When I am saying that steel is a solid solution and Fe3C is a compound, the first thing is you never listen to the chemical formula of steel. So for solid solution, there is no chemical formula. For compound, I am giving you this formula. So compound have the chemical formula, solid solution do not have the chemical formula. Why compounds? Why compounds have? Why they don't have? Because they are made up of percentage weight basis. We always say if carbon amount is less than 2% in the iron, we will call it as steel. Any amount, 1.8% of carbon in iron, it is steel. 0.8%, it is steel. If more than 2%, it is cast iron. Then also no formula is there. So cast iron, steel, both are solid solutions. Then for compound, they have chemical formula because they are made up of molar volume basis. Like 2 times of hydrogen, 1 of oxygen will give you 2 of water. Na plus Cl are valency basis. So either valency or molar volume basis, when things are made up of, they are said to be compounds. So they have the chemical formula. My dear, I already told you, when we are talking about steel, it is less than 2%, means variable composition is there. Carbon can be 1%, can be 1.5%. So variable composition means solid solution. Here, if you will be varying the composition, like if we are saying H2O and H2O2. So here 1 mole of oxygen, here 2 moles of oxygen. So guys, if the amount will change, water and hydrogen peroxide are different. You cannot drink hydrogen peroxide in place of water. So if you are going to change the chemical composition, in compound the entire thing will change, but in solid solution variable concentration is always found. If we are talking about solid solution, they always melt not at a constant temperature but in a range of temperature. Generally people thinks all the phase change operation are isothermal. It is not like that. In solid solution, melting, this is temperature time diagram. Let us say we are having let us say a liquid here. Then liquid is converted into liquid plus solid, it is converted into solid. Then liquid plus solid, when liquid is converting into solid, this is not a isothermal process in solid solution. But in compound it is isothermal process. Pure metal also shows the same relation, same temperature time diagram. Temperature time diagrams are said to be the cooling curves. You can see how 3 to 4 points I am covering along with. Are you getting it? When we are going to read the solid solution, they are read as minor element into major element. Like steel is a solid solution of carbon in iron. Whereas compounds are referred as major element and minor element. Like Fe3C is a compound of iron and carbon. Then my dear, example of solid solution is steel, cast iron, ferrite, austenite, like that. And when we are talking about the compound, the example is Fe3C, Mg2Bb. These all are the examples. My dear, if you compare the steel and Fe3C, Fe3C is a compound, steel is a solid solution. Solid solutions are found to be relatively ductile than the compounds. Is it clear? So guys, solid solutions are made by mutual dissolution. If you are going to add add sugar into water, then sugar and water both are mixing into each other, solid solution. But in compound, things are made by chemical reactions. Okay, I feel everybody got this wonderful things about solid solution and compound. Now my dear, solid solution, this is a very important topic going on. Questions are coming from Hume-Rothery rules. So try to be there for some 15-20 more minutes so that you can get that important rules. Yes guys. And everybody is getting it or not? No comments in the comment section. आ रहा है कि नहीं? पंकज, संदीप, पायश, गणेश, अरुण, राजश्री, ऋषिकेश. Great. So guys, now we are talking about when we are solid solution, when we are thinking of solid solution is something when we are having sugar and we add into water. Sugar will be dissolved into the water. When sugar will be dissolved into the water, my dear, then you know, if you will add 1 spoon, 2 spoon, 3 spoon, after some time, it will not be getting dissolved. After some time, it will stop. Why? Because solubility have a limit. Solubility is limited. but it increases with temperature and pressure. So if you will be increasing the temperature, then you can even dissolve 5-4 more spoon of sugar into water also. So what do you mean by that? It simply means that solubility has some limitation. You cannot add any amount of solute into solvent. Solubility is always there. But at high temperature, high pressure, solubility increases. But my dear, if you are making the jalebi, you need the sugar water. For that, you are going to have equal amount of sugar, equal amount of water. Then you are going to heat it to increase the solubility and it becomes a liquid. Sugar water, chasini. In that you can put gulab jamun, you can put jalebi. And my dear, if you are going to take the hot jalebi, it's fine. If you will keep it cool, keep it to the room temperature after some time. On the next day, you will feel jalebi is having some white things onto it. What is that? Because when it comes to room temperature, my dear, solubility of sugar in water reduces. So sugar come out of water. That is why you will feel that white particles are coming out from the jalebi. That is precipitation. So my dear, what is the point now? Actually, we want more and more solubility at room temperatures. Otherwise, after coming to room temperature, precipitation will become. They are not good. We never want precipitation to happen. So my dear, what is our desire? Our desire is to have a good solubility at room temperature. And if you are looking for a good solubility at room temperature, then my dear, it will be depending on very large number of factors. We were not aware of that because we wanted more and more solute to add into solvent, because more solute means more lattice distortion, means more strength in the material. So keeping that into mind, my dear, the god of this field are said to be the Hume Rodri. They have given some rules to increase or to get the maximum solubility. They simply said no one can give you 100% solubility for every case, but yes, we can tell you the conditions for which you will get the maximum solubility. And the first rule says the crystal structure factor. They said if you will be adding FCC into FCC, BCC into BCC, you will be getting the maximum solubility. You may be saying, sir, just some minutes back you were saying BCC elements are grain size refiners, and if I will add BCC into FCC, it will increase strength. But guys, that was a different method to increase the strength. That was grain size refinement. But if I want to increase the strength by lattice distortion, then I need to have FCC into FCC, BCC into BCC. First rule of Hume Rodri. Second Hume Rodri rule says that the difference in the atomic radii should not be more than 15%. If less than 15% size difference is there, it will be very easy. Why? Because if void is smaller, atom will be bigger, it will cause more distortion. That is why atom should be of similar size, that of impurity atom. More distortion will happen. Third is chemical affinity. There should not be any affinity of chemical reaction. Otherwise, compound will be formed. Next is relative valency factor. Relative valency means an element with lower valency, an element with higher valency. So my dear, A can dissolve more amount of B. B can dissolve less amount of A. So A should be solvent, B should be solute. Is it clear? If we are having solute smaller size, solvent bigger size, carbon smaller size, iron bigger size, it is said to be interstitial solid solution. If we are having solute bigger size, solvent smaller size, it is substitutional solid solution. Means if impurity is if impurity is smaller size, it will result into interstitial. If impurity is bigger size, it will result into substitutional. This is the end of, my dear, the solid solution strengthening. Now we are telling you, we are going for composites. I already told you in composites you may have two known metals. In composites, I already told you that there are always multiple phases. In composite, if we are talking about two important phases, then my dear, one phase is said to be the continuous matrix phase, and second phase is said to be the discontinuous reinforcement phase. It is like Monday to Friday you take normal food. In the morning some nasta, in the afternoon some roti, chapati, sabji, like that. But on Saturday, Sunday in the hostels, you have special items. Maybe some special sweet, maybe puri chole. Yes or not? Dear, just let me complete, because you can have the break once Ashutosh sir will come. I will complete it in 15 minutes. Okay, after that Ashutosh sir will come, then you may have break at 1:30 or 2 p.m. Okay. So, shall we continue right now? So guys, composites are always having two phases. One is continuous, like Monday to Friday normal food is going on. Saturday, Sunday we want some special food. Puri chole, some sweets, chole kulche, that kind of some special thing we want on Saturday, Sunday. To change the mood. If every day you will eat the same, it will be monotonous. And if every day you will be taking special, it will harm your liver and all, because it is too oily to have everyday puri sabji and all. So that is why we are having normal matrix phase. Then to improve the strength, in between we will be having some reinforcement to increase the properties. So my dear, composites are made up of three categories. One is particulate composite, other is fiber reinforced, third is laminated. Like whatever I have said, the same thing is written here. For sample, I am taking one theory part, composite. So guys, that's what I am saying. Similarly, you are having ceramics, polymers in this PDF. So composite I am teaching. Rest two topics you can read from the PPT. It will be very easy for reading, and after reading that you will get each and everything. And if still time left after Ashutosh sir, I may take those topics also. But those topics are something which you need to study. So first of all, we will be talking about the particulate composite. What is particulate composite? In this you will be having a molten metal of aluminium, copper. This is molten aluminium and copper. Now my dear, what I will do, this molten aluminium or copper is acting like the continuous matrix phase. Now what I will be doing, I will be adding some hard particle of tungsten carbide or silicon carbide, which are hard phases, and their melting point temperature is 3 to 4 times than that of the aluminium and copper. More than 3500 melting point temperature for tungsten. Tungsten carbide is still more. So if you will be adding that element somewhere, and after adding those elements you will stir it, then these particles will be mixed up. And my dear, when they will be mixed up, after solidification, when you will see the complete structure, you will be having the continuous phase of aluminium and copper. In between somewhere, you will be having the tungsten carbide particles. So when any crack will be generated, that will be stopped by tungsten carbide particle, because they are hard phases. So this is how the strength of the material have been increased. There is no chemical bonding here. Pugati, I am having that, don't worry. So when we are going to have that, my dear, those tungsten carbide and silicon carbide particles, they will be definitely increasing the strength of the material, and they will not allow the crack to move ahead. So they will be stopping the crack. So when they will be stopping the crack, my dear, this is how they increase the strength, and that way of increasing the strength is said to be the particulate composite. So my dear, in this particulate composite, whatever happened actually, it is said to be dispersion strengthening. So in the ESE paper, you may have a question that the strength is increasing in the particulate composite by which of the mechanism? The answer will be dispersion strengthening. Second is we are moving to the fiber reinforced. What is the fiber reinforced? I am telling you, my dear, in fiber reinforced you will be having the complete matrix phase. In complete matrix phase you will be having some thread like structure of some very good material, that is said to be reinforcement phase. Always remember, reinforcement phase should have high or better properties than that of matrix phase, because if I say Monday to Friday you will be getting the simple food, on Saturday Sunday we will provide you the special food, and in that special food if I will provide you dalia khichdi, which is even simpler than the normal food, you will not like it. So if you are adding some reinforcement, that should be better. That should be better in properties. Like that special food should be better in taste than the normal food. So guys, similarly, when we are talking about the fiber reinforcement, fiber is a thread-like structure. It is a thread like this, which will be having some length and some diameter. And when you will be putting that thread, that should have more Young's modulus than that of the normal materials. Is it clear? So when you are making that, the overall Young's modulus of the composite will improve for sure. So if we are going to have the longitudinal loading, like you can see loading is in the direction of the length of fiber, then the equivalent Young modulus of the composite is given by this. EM is the Young modulus of matrix phase, EF is the Young modulus of the fiber phase, reinforcement, and VM is the volume fraction of matrix phase. Volume of matrix plus volume of fiber. Similarly, what is the volume fraction of fiber phase? That is volume of fiber, but a volume of matrix plus volume of fiber. If loading is lateral in the perpendicular to the length, then this is the equivalent Young's modulus of composite. Is it clear for everyone, guys? Please tell me. Are you getting it, Ganesh, everyone? Next is the laminated composite. If you are going to make a layer over other, like when you take the mobile, you are going to have a tempered glass layer. That is the lamination. Why you have that? If something breaks, it should break. Mobile phone screen should not break. That is the purpose there. But here the properties is to improve the surface properties. Like my dear, if you are going to increase the surface corrosion resistance, so corrosion resistance, wear resistance, fatigue resistance, creep resistance, electrical and magnetic properties you can increase by putting a layer of material over other. Like if you want to increase the thermal conductivity, you can add a copper layer over the steel. Okay, so likewise, if you want to improve other properties, you may have aluminium clad over aluminium, copper clad over steel. So likewise, cladding means a layer of that material is given. That is said to be laminated composites. Okay. So guys, in laminated composites, this is how the properties are getting increased. Please tell me everybody got it. So we covered strengthening mechanism, solid solution, composite, everything. So guys, now we are moving to the, so actually I have added 2 times all the chapters. One is with the annotation, other is without the annotation. Okay, so this will help you. So guys, everybody got it. Now we are moving to the next chapter, that is phase diagrams. And when we are talking about the phase diagrams, to understand the phase diagrams, I would like to tell you that there are 4 types of system which we need to study. Great Sandeep, great Pankaj. Okay, so Arun, fine. Okay, so guys, now we are moving to the phase diagrams. When I am talking about the phase diagram, I would like to tell you guys, here we need to study the phase diagram of the systems where we have 2 elements. So that is why those phase diagrams are said to be binary phase diagram, because we are going to have 2 elements. Phase diagram is the diagram between temperature and composition. Here I will be having temperature, here I will be having percentage composition. So on y-axis temperature, on x-axis temperature composition we will be having. So this is temperature composition diagram. We will call it as binary phase diagrams. So guys, we need to study it for the 4 types of system. The very first type of system is isomorphous system. Isomorphous systems are those systems in which the 2 elements A and B, they are completely soluble in liquid state and completely soluble in solid state too. Completely soluble means any amount of A can be mixed with any amount of B. Like you can add any amount of milk with any amount of water. Mixing will be very easily done. And the same you can solidify. After solidification, you will not get water and milk separate. They will solidify as it is. So that is isomorphous system. If you see the practical example, copper, nickel, silver, copper, molybdenum, tungsten, this will come in the question. That molybdenum, tungsten is which type of system? It is isomorphous. Completely soluble in liquid state, completely soluble in solid state. Moving to the next case. Okay. So let us see the second type of system also. If we are talking about the eutectic systems, then my dear, eutectic systems are those which are completely soluble in liquid state and completely insoluble in solid state. In liquid state, they are like you will not be able to identify which one is A, which one is B. In solid state, you will clearly be looking at this is A, this is B. The example for those systems are lead, arsenic, bismuth, cadmium, gold, silicon. These examples you need to remember. Then we have the third type of systems, my dear. I will be telling you phase diagram also. The third system is partial eutectic system. So in partial eutectic system, you will be having complete solubility in the liquid state and partial solubility in the solid state. And the example for that is lead, tin and lead. Is it clear or not? Is it clear or not? So this is partial eutectic system. And the last one is two-layer system. They are neither completely soluble in solid state nor in liquid state. They are completely insoluble. In liquid they will be different, A and B. In solid they will be different, A and B. Neither you will be able to, you will be able to identify both of them separately in both the phases. So this is said to be the two-layer systems. Now my dear, I will be going one by one to the phase diagram. First we will see the isomorphous system, and let us start the isomorphous system. Then my dear, to make a phase diagram, we need to go for thousands of cooling curves in the laboratory. So what is cooling curve? Cooling curve is a temperature time diagram. So we are going to have 1000 or more than that temperature time diagrams. We are going to make temperature time diagram for different composition. Only one diagram I will explain there. Okay, rest is similar, only cooling behavior you need to see. So guys, when we are talking about this first type of diagram, isomorphous system, I am taking two components A and B which are completely soluble in liquid and solid state. The melting point temperature of A is M, for B is N. Okay, so I am taking M to be less than N. Let us say I am having 100% A. Pure metal is showing solidification at same temperature. So this is for 100% of A. You can see I will be having this point as L0, this point as S0. So liquid is getting converted to solid at the same temperature. The curve is coming isothermal. If I will add B into A, my dear, it will become a solid solution. I will be having a range of temperature. This time I will get two different points here. This is L1, this is T1. This is 90% A, 10% B. If I will continue this, once again I will get Ln Sn, because this is liquid plus solid, this is solid. So guys, this will be the same temperature as that of N. Okay, so this temperature is the N. So guys, likewise I have made thousands of cooling curves and I get a lot of these temperature values. Now I will be collecting all the L points, L0, L1, L2 up to Ln. I will be collecting all the S points, S0, S1, S2, Sn. Because I need to plot these all the points in terms of temperature and composition. So I got the temperature for L0, temperature for L1, temperature for L2, temperature for Ln, temperature for S0, temperature for S1, temperature for S2, and I will start plotting them. I will be plotting L0 and S0 was at the same point, Ln and Sn was at the same point. Then I know this is L2, this is S2 corresponding to some composition. And when I will be plotting all the L points, this curve will come. All the S point, this curve will come. So above this everything is liquid, below this everything is solid, in between liquid plus solid. This wonderful diagram is said to be the phase diagram. Please tell me you got it or not, guys. This wonderful thing is said to be the phase diagram. This wonderful thing is said to be the phase diagram. So here I will be telling you the rules. The number one rule is said to be the tie line rule. Questions are coming from the tie line rule. Tie line rule. So guys, when I am talking about the tie line rule, tie line is the constant temperature line. Tie line is the constant temperature line. And my dear, if you see this constant temperature line, this is cutting at this point and this point. So if you have any composition in between this is liquid plus solid, so you will be having some amount of liquid, some amount of solid. Tie line rule said that I cannot help you with the amount of liquid and solid, but I can help you in one thing, that whatever be the amount of liquid, it will be having this composition, and whatever be the amount of solid, that will be having this composition. So we are able to get the composition of liquid phase and solid phase using this tie line rule. Similarly, another rule was given, that is said to be lever rule. From this lever rule, this year question was there in mechanical paper also. So if you talk about the lever rule, what it is? Lever rule says that if we are going to have a particular composition, then if this is C, this is D, this says take that line separately, CD. And we are talking about a particular composition Z star. This will be giving a point F. Then my dear, you know this is cutting at liquidus, the line joining all L point, solidus, the line joining at all solid point. So my dear, it says that here it is liquid, here it is solid. So if you want to find out the amount of liquid, this rule says that amount of liquid is given as FD by CD into 100. And similarly, amount of solid is CF by CD into 100. Please tell me, guys, everybody got this or not? Payash, Pankaj, Sandeep, everybody got it or not? Please tell me that. Please tell me that everybody got it or not. So guys, these were the things which generally student face difficulty and student need to understand, and major questions are also coming from this part. Now I would like to say something. Let me see first of all whether Ashutosh sir is there or not. Let me check. Okay, because I feel Ashutosh sir is waiting. Okay, so let me check. Yes, guys. So first tell me whatever we have discussed till now. We understood this or not? We understood this or not? Please tell me whatever we have discussed from the morning. Have you got everything or not? Hello?
Yes, sir.
Hanji, sir. So guys, everything you got it or not? Please tell me that. So guys, we were talking about... Just wait. Yes. So guys, we were talking about all the things what we have studied. We have studied crystal structure. We have studied crystal defect. We have studied strengthening mechanism. We have studied phase diagram, one type of phase diagram. So guys, now I feel after that we are having three more types of phase diagram and iron carbon diagram. If you want to study that in detail, for ESE paper 1 it is not required. For other branches, they will not be asking you that in-depth thing. But still, if you want that into more depth, I have already taken the marathon on material science. Just I feel in the 29th or 30th January, that is available there. If you want to study complete heat treatment, triple T diagram, and also iron carbon diagram and 3 type of rest phase diagram, you can refer that video if you want to go into detail. Otherwise, if you study up to that, you just need to see the cooling behaviors. Other things are not coming in the paper. But still, if you want, you can refer that video. I will share the link of that video here only. And I will also share the link of my Telegram channel where you will get this PDF. We have studied composite also. So rest, as I said, 1 to 2 theory topics we have left. That is polymers, that is ceramic. Otherwise, my part will be going on till 5-6 p.m. Then Ashutosh sir will be coming. He will be continuing till 10 p.m. Then when you will revise. So it's better कि इसके आगे जो है Ashutosh sir अब command ले और sir please आ जाइए आप. So sir will be continuing now electrical and magnetic properties and complete electrical part. So sir, over to you.
Yes, sir. Hi guys. How are you? I was watching this session and Dheeraj sir has given very interesting examples from fruit. I think you were talking about gulab jamun and jalebi. So nothing can be better than this. But sir, I think this is enough. This is enough. What we are doing, it is more than enough because in one session you cannot expect everything to be covered. It's about important things which are most frequently asked in the examination that you have to cover first. Okay. So, sir, I think they were asking for a break. So, what I'm thinking is, all the students who want a break for 5-6 minutes, you can just go, and rest of the candidates who are live with me, they can ask their queries, general queries about engineering services or any queries if you are having related to subject also, and apart from the subject, if you have any query, you can ask me.
Sir, अभी mic लगा लेंगे तो voice सही हो जाएगा. Don't worry. Sir, please.
So, any candidate who wants a break because sir is taking the session from 10 a.m. So, just 5-10 minutes, 5-6 minutes, you just go.
Even sir, I would like to add, like Tej Prakash Yadav is asking, dear, if you will complete all the marathon session, what I feel is we are covering all the major important topics, and even for polymers and that ceramic, these are the 2 topics which I have not taken right now. So for that, I will share you the PDF. Even if I will go through that, you need to mug up that only. So whatever we are covering, not only 80, you can score more than that because mathematics, aptitude are more scoring. Current affair already yesterday happened. Material science over whatever you have seen, the questions will be moving around that only. Okay, and if you still want to study the extra part in the PDF that will be available, hardly you will be requiring 1 to 2 hours for reading out that you need to mug up only. Okay. And sir, please continue.
Sir, one candidate, he was asking, I was watching your session, he was asking that after attending this marathon session, will be able to score better in the GS.
Yes.
So, what you are thinking? You are thinking some black magic here that I will give you, मैं तुम्हें बिल्ली का नाखून दूं काले कपड़े में बांध के तब जा भैया यही करना है तुमको. There is no shortcut to success. You have to be there, you have to attend the sessions, and these sessions are not just for those candidates who have already prepared, because it will be like a revision. The way sir was explaining the concepts, it was so interconnected that even if you are reading it for the first time, then also at least average questions you will be able to handle. So I think these marathon sessions are extremely important, and we have done it same for the GATE examination also and for engineering services also. So thank you so much, sir, for your efforts, and I think guys must be enjoying your session. And now I am going to continue the session. So thank you so much, sir.
Guys, now continue, and Ashutosh sir अभी समा बांधेंगे.
No.
तो आपको और भी मजा आएगा.
Yeah, it's okay, sir. I will put it. No problem, sir.
सर इसको सेव करना है.
Save कर ले.
ताकि स्टूडेंट्स को मैं शेयर कर दूं.
Save it. So guys, if you want a 5-6 minutes break, you can just go and come back again, and I will be taking up the students' doubt. If you have any doubt, you can ask me. General doubt, technical doubt, non-technical doubt. Downloads. Perfect.
Send कर दीजिए सर.
Yes.
Thank you sir. Continue.
Thank you, sir. So guys, I will be taking up the electrical and electronics part. So majorly I will be focusing on the dielectric portion and the magnetic properties, because that is the major portion from where questions can be asked. And there are some small portions. Those portions I will be leaving, because another session I am planning for material science, which will be for core subject, that is for EC electrical students, related to semiconductors and conductivity. So that portion you can cover, I think maybe tomorrow or day after tomorrow I will be planning the session, so you can attend that session and you can complete those things, because otherwise it is going to be a very long session. Okay. So guys, you were enjoying the session like anything. I was watching the session, and Dheeraj sir was really into the subject, because he was giving so many interesting explanations. It must be quite easy for you to remember things. Yes or no? Just one moment, let me put up the slide. Perfect. Yes, guys. Dheeraj sir will be just sharing his Telegram channel link. Okay, so don't worry. Yes, Tej Prakash, ethics will be planned, and most probably, I think tomorrow. Okay, most probably tomorrow. You will be informed already. We have discussed with the team, and definitely it will be planned. Don't worry about it. Is it clear, everybody? So let us start with the session. If you have any more doubts, see, if you want me, I can give you just 1 or 2 minutes motivation for the engineering services examination, because I have been in this journey, because I was also preparing for engineering services sometimes when I was at your age. Then I get into the teaching profession, mentoring hundreds and thousands of candidates every year. See, if you see engineering services examination, it's not examination which you can say that you will appear and you may qualify or you may not qualify. Listen my words very carefully. Engineering services is an examination. This may happen in the GATE examination. Even if you have done a very good amount of preparation, there is a possibility you may get a rank what you desire or deserve, or may not. But engineering services examination is like that. If you have done a good amount of preparation, before you are appearing in the examination, you will have this feeling inside that yes, I am going to get through in this examination. Maybe this time you are not having this feeling. Suppose most of you might not be having this feeling this time. I accept it. But what about next year? So this year you have to give your 100% effort and see what level you have achieved. And if you succeed, then what can be better than this? And if you don't succeed, then still you have achieved some success, partial success. And what is the remaining gap that you have to fulfill in the next coming year? And 2024 is going to be your year. Are you getting that? So things are not going to be happening in just one go. You have to make constant efforts, consistent efforts. Yes, Maniket, as per your requirement, I can speak Hindi and English both, no problem. हिंदी में भी बात करेंगे, इंग्लिश में भी बात करेंगे. जहाँ पर भी आपको लगता है आप मुझे बिल्कुल खुल्लम खुल्ला टोक सकते हैं, आप मुझ पे अपना पूरा अधिकार जता सकते हैं कि सर आप हिंदी में बोल दीजिए, सर आप इंग्लिश में बोल दीजिए. So it's not going to be a problem. But before we actually start, I want all of you to just share this session with your friends and colleagues, because there was a technical glitch. I was watching the session, and that is why the number of students drastically reduced. So just one more time, you just quickly hit the like button and share the session with your friends and colleagues. So guys, let us start GS paper 1. Another important subject, that is material science. Already I think 60-65% subject have been covered by Dheeraj Sardana sir, a great faculty, a legendary faculty for material science and other mechanical subjects. Now I am going to talk about the portion which is related to electrical and electronics. Before I start, there is one important mega workshop which is being taken by everybody's favorite and my favorite also, Abhinav Negi sir, and this is going to be scheduled on 14th of February, that is today itself. The timing is 7:30 p.m. The idea is how to ace GATE 2024 in the first attempt. So if you want to attend this workshop, please go to the BYJU'S Exam Prep app and get yourself registered for this workshop. And once again, we are coming up live on 19th of February for the complete live analysis. It's okay, Sarika? Okay. So 19th of February, the same day when your examination is there, paper 1 we will be discussing right at 5 p.m. and paper 2 6 p.m. in the evening. So subscribe to BYJU'S Exam Prep so that you do not miss these important sessions. Now 15th of February, BYJU'S Exam Prep rank predictor is going to be live when your GATE response sheet is going to be available. So subscribe, you have to register yourself so that you can avail this facility. Hundreds, thousands and lakhs of students are going to follow this. So you will be getting a better idea about your possible rank and you may take better decisions in terms of your career. So let us start with the subject and I will be starting from dielectrics. So the first thing you have to understand the difference between dielectrics and insulator, because if you see dielectrics and insulators, they are the two phases of the same coin. These are the same class of non-conducting materials. Dielectrics are also non-conducting and insulators are also non-conducting. So what is the difference? The difference is in terms of their application. What is the difference? When you talk about dielectrics, we are saying it is a non-conducting material which gets polarized in the presence of external electric field. Now, because there may be students who are from non-electrical and electronics background, so for those candidates, let me tell you what is the meaning of this statement. Suppose you have a material like this, okay? Now, this material is going to have dipoles which are randomly oriented. Are you able to see this? The orientation of the dipoles is going to be random in nature when there is no electric field. Now suppose you apply some electric field which is non-zero. So what will happen? These dipoles are going to align in the direction of external field and this property of the material we are calling as polarization. Is it clear? Everybody just tell me yes or no in the comment section. Now, when we talk about insulator, this is also a non-conducting material which provides electrical isolation. Electrical isolation means what? Suppose I give you the example of transmission tower. You all must have seen when you are going from a highway, you must have seen the transmission tower. The most simple type of insulator you can say. So this is your transmission line in which electrical power is flowing and these are the insulators. So these insulators provide a electrical isolation so that the current which is flowing in the line is not bypassed or lead to the transmission tower so that it becomes dangerous for the nearby people. Yeah, it's okay. Is it clear, everybody? So what is the difference between dielectrics and insulator? The only difference is in terms of the application when you are focusing on material getting polarized. And when material gets polarized, what does it mean? Let me take the example of parallel plate capacitor. Suppose there is a capacitor. So how we define the capacitance? It is epsilon naught A by D, where A is the area of the parallel plate and D is the separation between the two parallel plates. Now suppose you are going to fill the gap between the two plates with some dielectric material having the dielectric constant or permittivity as epsilon R. So what is going to be the capacitance now? Now capacitance is going to be epsilon naught, epsilon R A by D. Now this epsilon R is greater than 1. It means by putting the dielectric material in between the two parallel plates of the capacitor, your capacitance value is increasing. What is the meaning? When your capacitance value is increasing, it means what? The energy is stored in the capacitor is given as half CV square. So if capacitance is increasing, the energy stored in the capacitor is increasing. So when you are talking about the energy storing capability of the material, then you are talking about dielectrics. When you are talking about the electrical isolation, then you are talking about the insulators. This is the major difference. Is it clear for everybody? Is it clear? Now let us talk about the parameters of dielectric. If you talk about the parameters of dielectric is nothing but some basic properties which are going to tell you that why different dielectric materials have different unique properties. Is it clear? So the first one is dielectric constant, then we have dipole moment, then we have polarization, and then we have polarizability. The first one is the dielectric constant. Now dielectric constant is defined. Dielectric constant is defined as the ratio of electric field density and the electric field intensity. Now this epsilon you can write as epsilon naught, epsilon r, where epsilon r is the relative permittivity of the material, and epsilon naught is the permittivity of free space. Okay, let us talk about the dipole moment. How we are defining the dipole, that is important, and then we will be talking about the dipole moment. Yes, its value is 8.85 into 10 to the power minus 12 farad. So dipole we are defining as a system of a positive and a negative charge separated by a very small distance. Now very small distance is important here. Why? Because if the distance is going to be quite large, why it is not possible? Because there will be a force of attraction between the positive charge and the negative charge. So ultimately they have to collapse, but they are not collapsing. Why they are not collapsing? Because when the distance is very small, when the separation between them is very small, then there are interatomic repulsive forces which are going to balance out the electrostatic attractive force, and then you will get a stable system. That is why this small distance is important. So you have a positive charge, you have a negative charge separated by a small distance d. So how you are defining the dipole moment? Dipole moment is defined as the product of the individual charge magnitude multiplied by the separation between them. So this is going to be coulombs meter. Is it clear, everybody? Let us talk about the polarization. Now polarization is going to be the sum total of all the dipole moments per unit volume. Suppose you have a material like this. Suppose you have a material like this. Now there will be number of dipoles randomly oriented. Something like this. Now these individual dipoles are having the dipole moment small p, and how you are defining the polarization? You are defining the polarization as n into p. What is this n? This n defines the number of dipoles per unit volume. What is going to be its unit? Its unit is going to be coulombs per meter square, because n has no unit, it is per unit volume, so it is 1 upon m cube. यस मनिकेत, ये आपने 12th में पढ़ा होगा काफ़ी कुछ, बट थोड़ा सा अलग भी हो सकता है, बट काफ़ी कुछ बेस वही है, जो उसका बेस है, बैकग्राउंड है, वो वही है. सो धीरज सर ने आपको पीडीएफ का लिंक दे दिया है अपने टेलीग्राम चैनल पे. ओके, तो धीरज सर दूसरे वाले चैनल पे भी एक बार आप डाल दीजिएगा, ठीक है? तो दोनों चैनल्स पे अभी धीरज सर आपको पीडीएफ प्रोवाइड कर देंगे टेलीग्राम पे, और मेरा जो सेशन कंप्लीट होगा उसके बाद फिर मैं आपको पीडीएफ प्रोवाइड करूंगा, ठीक है? So this is going to be the polarization P, capital P, which we are talking about here. And this is defined as the total, sum total of all the dipole moments per unit volume. Is it clear, everybody? Now, if you want to relate, just a moment. Okay. Suppose you want to relate the electric field density, so it is going to be epsilon naught E plus P. This is the relation. How it is defined? Suppose you have a material and this material, some external field is there which is non-zero. Now what will happen? All the dipoles inside this material is going to be aligned in the direction of external field. So what is happening? The electric field density inside this material is going to be because of two components. The first component is flux density due to external electric field, and the second component is density due to polarization. I hope you are getting this. So you have one more equation. You know that D is equal to epsilon E also, or you can write epsilon naught epsilon R E. Just put this value here. So if you put this value here, it will become epsilon naught epsilon R E, and this will be epsilon naught E plus P. So can you separate E and P? Yes. So P becomes epsilon naught epsilon R minus 1, and this will be E. Now this epsilon R minus 1 we are defining with a new parameter or new constant, which is defined as the electrical susceptibility of the material. Electrical susceptibility of the material. Is it clear, everybody? So these formulas are going to be important. You may get a direct question on this. You can write for xi E also. Xi E is going to be what? This is going to be epsilon R minus 1. And if you want to write the relation between P and E in terms of xi E, then I am writing it here. It is going to be P is equal to epsilon naught. This is xi E and this is E. Everybody just tell me in the comment section. If you have any doubt till now, you can ask me. Yes, everybody. If you have any doubt, whatever we have discussed till now, you can ask me. See, we have defined the polarization capital P as number of dipoles per unit volume multiplied by the dipole moment of one individual dipole. So you will get total dipole moment per unit volume. Now, if you relate it in terms of the electric field density, you will be getting two components: electric field density because of the external electric field and the polarization in the material. Is it clear? So these formulas either you remember, or in the examination, if you want, you can go with the derivation also if you have a little bit of confusion, if you are not confident about it, because for non-electrical electronics. Yes, this is for 19th. Now let us talk about the polarizability. We are representing it with the parameter alpha. Now please understand what happens. Suppose you take the example of an individual atom. So what is the structure of the atom? The structure of the atom is that at the center there is a nucleus. Nucleus is having neutrons and the protons, and nucleus is positively charged because of the protons. Around this nucleus in the elliptical orbits, the electrons are orbiting in different orbits. Now, the electrons are represented by the electron cloud, and the center of that electron cloud is represented by this equivalent electron center. This orange one. You see that? The blue one represents the positive charge center. Now, this is the case when there is no electric field. When the external electric field is 0, then this is the situation that the center of negatively charged electron cloud coincides with the nucleus or the center of positive charge when there is no electric field. But when there is electric field, when there is external electric field present, what will happen? The positive charge, suppose the electric field is in this direction. So what will happen? The positive charge will be displaced somehow in the direction of external electric field, and the negative charge will be displaced opposite to the direction of electric field somehow. Why? Because F is equal to QE. So if the value of Q is minus Q, then the force is going to be opposite the electric field. If the Q is positive, then the force is in the direction of electric field. I hope you understand. Now, this separation between the center of positive and negative charge is going to be decided by what? This is going to be decided by the external electric field. The more amount of electric field you are going to apply, the more is the separation. Now, how you are defining? Now, there will be a induced dipole. This is the induced dipole. Why induced dipole? Because this dipole was not present here. And because of the application of external electric field, now because of the separation, now there will be some induced dipole moment, and it will be directly proportional to the separation. Because the charge is not changing. Charge is constant, whether it is a positive charge or negative charge, this is constant. But the separation between them, d, is variable. So this individual dipole moment is directly proportional to the separation distance d. And this separation distance d is directly proportional to E. So can I write this individual dipole moment small p is directly proportional to E? Yes or no? Now if you remove the proportionality constant, it will become alpha E. This alpha we are defining as polarizability. Is it clear, everybody? Let's go to this, and if you have any doubt, you can ask me. See, don't fight with each other. Sarika and Maniket. Okay? Everybody, you please do your own business. If you have any doubt, you can ask me. If you don't have a doubt, then enjoy the session. And if you don't want to enjoy the session, you can leave the session. Okay? But don't do these type of stuff. Is it clear, everybody? So now if I again write some of the equations which may be asked in your examination, listen carefully. How you were defining the polarization? You were defining the polarization as N into P. Yes or no? Number of dipoles per unit volume multiplied by the individual dipole moment. But just now you have seen that small p is alpha E. So just put this value here. So you will get the polarization P as N alpha E. Yes or no? Is it clear, everybody? Very important equation you are getting. N alpha E. Now you have one more equation. That equation is P is equal to epsilon naught xi E E. Just compare these two equations. If you compare these two equations, what you will get? You will get xi naught epsilon naught xi E is equal to N alpha. So can you write alpha? Yes, it is going to be epsilon naught xi E divided by N. So this is how alpha and xi E are going to be related. Now if you want to understand what is the physical significance of this polarizability alpha, how you are understanding actually what alpha is doing here. So please understand. Alpha is telling you the ability of the material to get polarized at the atomic level. Hello? Alpha is telling you the capability of the material to get polarized in the presence of an external electric field at the atomic level. At the atomic level it is happening. But when you talk about electrical susceptibility is also giving you the same information. How much electric field you apply, and how much polarization you are getting. But electrical susceptibility is talking at the material level. You understand the difference? No book will tell you this information. Polarizability is talking at the atomic level of the material, and electrical susceptibility is talking at the material level. Is it clear, everybody? Just tell me yes or no. Let us talk about the mechanism of polarization. What is the meaning of mechanism of polarization? We have just discussed that if an external electric field is present, then the material may get polarized. The dipoles are going to orient in the direction of external electric field. Now we want to understand how this phenomena is happening. So we have the mechanisms of polarization. The first one is electronic polarization. Then we have ionic polarization. Then we have orientational polarization. Then we have space charge or interfacial polarization. So let us talk about them one by one. If you talk about the electronic polarization, so from the name itself, you may understand that something is happening at the electron level. Yes or no? Something is happening at the electron level. Now see what is happening. It results because of the displacement of negatively charged electron cloud with respect to the positively charged nucleus. Now understand one thing very important, something very important. Just now when we were discussing about the polarizability, we have said that if you apply the electric field, the positive charge center will get displaced in the direction of electric field, and the negative charge center will displace in the direction of opposite the direction of electric field. But now he is saying it is the displacement of negatively charged cloud with respect to the positively charged center. Why? The simple reason is the nucleus is going to be extremely heavy in terms of its weight in comparison to the electron cloud weight. Yes or no? So if something is having more weight, the displacement will be less. If something is having less weight, the displacement will be more. So this statement simply tells you that the displacement of positively charged nucleus is not going to be that much. It's insignificant. And the actual displacement is the displacement of the negatively charged electron cloud. Is it clear for everybody? Just tell me yes or no in the comment section. Are you able to follow this or not? Hello everyone. Are you able to follow this or not? This understanding. Now listen very carefully. But here we are having one assumption. What is that assumption? I will tell you. This is the fact that actually the center of negatively charged electron cloud is getting displaced. Okay, but what is the assumption? What is happening? Your nucleus is concentrated. All the neutrons and protons, they are concentrated within the nucleus, but your electrons are all orbiting in elliptical orbits. So when you talk about the electron cloud, and when you talk about the center of such electron cloud, it is not that fixed, it is not certain. Yes or no? If you include the wave nature of electron, then it will be very difficult to understand where actually the electron is. So what we are assuming is, that no, electron cloud center is not getting displaced, the positively charged center is getting displaced. This is our assumption. Is it clear? This is our assumption. Please understand this very carefully. Now what is happening? Here the electric field was 0, so both the positively charged center and the negatively charged center, they were coinciding with each other. But when you apply some electric field, what is happening? There will be a separation. Now this separation, how it is decided? Suppose this is X. The separation between the center of negatively charged electron cloud and the displaced positively charged nucleus is X. Now how X is decided? Please understand. Please understand this. Let me add one page here. Then only we can discuss this. Okay. Okay. Now you will understand this because questions can be asked on this. So suppose this is the situation. This is the center of negatively charged electron cloud. Center of negatively charged electron cloud. And suppose this is your positively charged nucleus. Okay. Now understand one thing. How this distance x is decided? Please understand how this distance x is decided. Can you tell me? How this distance x will be decided? X will be decided by two forces. One force because of the external electric field. Suppose the external electric field, the force because of external electric field is in this direction. Yes or no? In the direction of external electric field. At the same time, there will be a force of attraction. A force of attraction between the center of negatively charged electron cloud and the positively charged nucleus. Yes or no? So the moment these two forces are going to balance out, that will decide the distance x. So can you help me? Can I write the forces? Yes. Can I write Fe? Yes. Ze is the total positive charge. Suppose Ze is the total positive charge. Now what is the force? F is Q into E. So Ze multiplied by external electric field is going to be like this. Now what will be the force of attraction between these two charges? This is going to be 1 upon 4 pi epsilon naught Q1 Q2. What is Q1? Suppose Q1 is the negative charge. So negative charge is going to be Ze. What is positive charge? Now understand very carefully. Understand very carefully. Understand very carefully. Sorry, this is going to be the positive charge. When you talk about the center of negatively charged electron cloud, for a radial distance x, you have to take only those electrons which are inside this distance, radial distance x. It means the charge of the electron cloud you have to rationalize. How? This is going to be x cube upon r cube. What is r? R is the radius of the atom. Are you able to follow this or not? Now divided by what is the distance between them? The distance between them is x, so it is going to be x square. This is going to be x square. If you simplify this, because we don't have that much time, so I am just directly giving you, you can see it. So x you will be getting as 4 pi epsilon naught r cube divided by Ze and capital E. This will be the relation you are getting for x. Everybody is okay with this? Mr. Gojo, that you are talking about composites and ceramics. So not composite, but ceramic is a part when we talk about the material science for ECE and electrical core students. Okay, not all the students. In this particular GS paper 1, whatever you are having for the material science, if composites and ceramics are there, so Dheeraj sir must be handling that. I think he is giving you the PDF, so you will be getting that. Because this composites and ceramics, I think it is a very small part. You can revise it on your own. Important things you can follow from here. Is it clear? So now because of this separation between the positive and negative charge, I want to write the induced dipole moment. What is going to be induced dipole moment? Any individual charge magnitude multiplied by x. So can you tell me what is ZEX? What is ZEX? 4 pi epsilon naught r cube. 4 pi epsilon naught r cube, and this is capital E. This is the induced dipole moment. Can you compare this equation with P is equal to alpha E? Now alpha becomes alpha E because it is electronic polarization. It is because of the displacement of the electrons. So if you compare it, you will be getting alpha E as 4 pi epsilon naught r cube. Everybody just tell me yes or no, are you able to follow this or not? 4 pi epsilon naught r cube. Is it clear, everybody? Now you can relate, because I cannot give you the exact derivation, but now you can relate, because you can define the polarization as N alpha E E. Yes or no? Yes or no? You can define it or not? Yes. And you can also define P as alpha naught epsilon r minus 1 E. So I cannot give you the actual derivation, it will be little lengthy. So you can compare these two equations. You know what is alpha E in terms of the radius of the atom. So you can relate, listen, you can relate epsilon r, that is the relative permittivity of the material, with the radius of the atom also. Is it clear, everybody? Are you getting that? Tell me in the comment section, are you able to follow this or not? Is it clear? Both the channels, tell me in the comment section. The next one is the ionic polarization. Now the name itself tells you that ionic polarization is going to be because of the ions. Yes or no? So when you have materials like alkali halides, for example sodium chloride, NaCl, you see there will be cations and anions. So cations are positively charged ions and anions are negatively charged ions. So what is happening? Again, when there is no electric field, positive and negatively charged ions will be at their original position. But when some external electric field is applied, now these are going to be displaced with respect to each other, because the positively charged ion will get displaced in the direction of external electric field and the negatively charged ion will get displaced in the opposite direction of the external electric field. And because of this displacement or the separation, you will be getting another dipole moment, that is, or you can say polarization, that is ionic polarization. Now, the important part of this is that if you talk about the electronic polarization, it is independent of temperature. It is independent of temperature. There is no temperature term in the electronic polarization. Now, if you talk about the ionic polarization also, ionic polarization is also independent of the temperature. It occurs in the ionic materials when the oppositely charged ions get displaced in the opposite direction. This type of polarization is generally found in the materials having ionic bonds, and this is the most obvious choice between the dissimilar atoms like NaCl and the alkali halides. This is also called as molecular polarization because ions are going to be involved. This is important. This is important. May come in your examination. They are called as molecular polarization. Ionic polarization is also independent of the temperature. Okay, and the total polarization is given as a sum of electronic and ionic polarization. For example, I will give you some idea. Suppose you are defining the total polarization as electronic polarization plus ionic polarization. Electronic polarization you can write as N alpha E, capital E, plus N alpha I, capital E. So you can simplify this. The total polarization is going to be N alpha E plus alpha I, and this is E. So this is going to be the total polarization for ionic and electronic polarization. Now for most of the materials, the ionic polarizability is smaller. Ionic polarizability is smaller than the electronic polarizability. What is the reason? The reason is because of the size and the weight of the ions is very, very large in comparison to the electrons. Is it clear? This is important. Now let us talk about the orientational polarization. Now again, the name itself tells you that it is because of some specific orientation in the material, because of which you are getting some dipole movement, and that dipole movement will contribute to the polarization in the presence of external electric field. So what is happening here? It is generally found in those materials which have partially ionic and covalent bonds. Partially ionic and covalent bonds, and it is found in materials having asymmetrical structure. Always remember, whenever you have asymmetrical structure, you will have permanent dipole moment. Something you can note down in your notebook. Why? Let me give you one example. Suppose you go to some public place and you see there is a man whose nose is 1 kilometer long. So for the rest of your life, you will never ever forget that man. Why? Because you have never seen such a man who is having a nose of 1 kilometer long. So whenever there is asymmetry, there will be permanent dipole. This logic you can use somehow if you understand. Take the example of water, H2O. So this O is double negative. This is H positive. This is, oh my God, what is this? Just a moment. Sorry, I think I have touched something. Now it's okay. Okay. So this is H plus, this is also H plus, and the angle between them is 104 degrees. So because of this specific orientation, they are asymmetrical in nature, and that is how they get the orientational polarization. The examples are mentioned. You can just take a reference: H2O, CO, NO, H2S, NO2, CH3Cl, etc. Now, how this orientational polarization is going to be defined? So again, let me add some pages. Okay. So if you talk about the orientational polarization, you have to remember this. Okay. It is given as orientational polarization is given as N alpha naught, and this is E, where alpha naught is PP square upon 3KT, where PP is the permanent dipole moment and K is the Boltzmann constant. And capital T is the temperature. Capital T is the temperature. So if you put the value, you can write it. P is equal to N PP square upon 3KT, and this is E. This is P naught, orientational polarization. So if you want to know if all the electronic, ionic and orientational polarization is present, then how you are going to define the total polarization, then you can write the total polarization as a sum of electronic plus ionic plus orientational polarization. You can write it N alpha E plus N alpha I E plus N you can write it as PP square upon 3 kT, and this is E. So if you simplify this, you can simplify this as N alpha E plus alpha I, okay, and this is going to be E plus N PP square upon 3 kT, and this is E, and this is the total polarization. Is it clear, everybody? If you have any doubt till now, you can ask me. Yes, everybody, tell me in the comment section, are you able to follow this? Just see it. Everybody is okay with that? Now you see, this total polarization you can again write in terms of the dielectric constant. So you can write epsilon naught, epsilon r minus 1, this is capital E, this is equal to N alpha E plus alpha I E plus N PP square upon 3 kT, and this is E. So now E is going to be cancelled everywhere, and you will be getting epsilon naught, epsilon r minus 1, that is N alpha E plus alpha I plus N, this is PP square upon 3K, and this is 1 upon T. So you observe, this is going to be the equation of a straight line. Can you observe this? Suppose this is Y. Okay. If you write epsilon naught, epsilon r minus 1 as Y and X as 1 by T, suppose this 1 by T is X. So this becomes the slope M, and this becomes the intercept at the y-axis, that is C. So if you draw this straight line, at the x-axis you have 1 by T, at the y-axis you have epsilon naught, epsilon r minus 1. Now this will be a straight line, something like this. Okay, but this is not going to be actually intersecting this y-axis. Why? Because at the point of intersection, 1 by T will be 0. 1 by T 0 means T is infinite. Now T infinite is practically not possible. So there will be not actual intersection. But if you extend it, if you extrapolate it, so this intersection will give you N alpha E plus alpha I, and the slope, okay, if you write in terms of tan theta, this is going to be given by this N PP square upon 3K. This is N PP square upon 3K. This is just for the sake of your reference if they are asking a good question. Okay, if they are going to ask a good question, then they may ask from this area. Now we are coming to the last mechanism of polarization, that is space charge polarization. Now space charge polarization, I will tell you, very simple, you will understand in one go. Now there is one cream in the market. Okay, don't take the name in the comment section, otherwise it's not good. Now that cream says if you apply that cream, so very soon you will become fair. Your color skin will become from black to fair. So it's something like this now. Suppose this is your skin, something like this. These are the irregularities, black heads in your skin, and they are going to remove, something like this. Now what happens? In general, in materials, there are some defects. Dheeraj sir was telling you about various types of defects. So one type of defect is the lattice vacancies. Okay, lattice vacancy means when a particular atom is not present where it has to be, that is a vacancy. जहां पर जिसको जिस समय होना चाहिए वो वहां पर नहीं है, तो वो हो गया vacancy. So because of the lattice vacancy or the impurities present in the material, what happens? What happens? Suppose there is one electron here. there is one electron here. Because of the application of external electric field, which is non-zero, suppose this electron start traveling in this direction. So because of this lattice vacancy or the defect or the impurity, this electron will get trapped into this like this. So there will be more and more number of electrons which are getting trapped inside this vacancy, yes or no, something like this. So there will be accumulation of electrons. Now initially there was no charge, and now because of the presence of external electric field, there is accumulation of negative charge, that is electrons. Now there will be equivalent image charge also. That equivalent image charge, positive charge, is going to develop a dipole because of the positive charge and the negative charge, and this induced dipole will contribute to the polarization. So this is the whole story about the space charge polarization. Now if you talk about the multi-phase materials, in multi-phase materials are those materials which are having the lattice vacancies. Okay, materials which are having lattice vacancies, they are called as multi-phase materials. So for multi-phase materials, the total polarization is given as electronic, ionic, orientational and space charge polarization. But if you have a single phase material, in a single phase material, the materials are not having the lattice vacancies. So when lattice vacancy is not there, then space charge polarization will be 0. When space charge polarization is 0, then the total polarization will be given as electronic, ionic and orientational polarization only. Bermuda Triangle. Okay. Everything is okay. Yes, everybody just tell me. Are you able to follow this? Is it clear? Why the number of candidates are so less? If you have any doubt, you can ask me. But if you don't ask me, how I will come to know whether what I am giving you is useful for you or not? Yes, everybody. Yes, sorry, I was putting the charger. Any doubt, any problem? Okay. Let us talk about the classification of dielectrics on the basis of their dielectric behavior in the presence of external electric field. So basically we are talking about the classification of dielectrics on the basis of external electric field. First we are talking about the piezoelectric materials, then we will be talking about pyroelectric materials, then we will be talking about ferroelectric materials, then we will be talking about antiferroelectric materials. From the name itself, I can tell you, okay, piezo I will discuss, okay, piezo I will discuss all. Now pyro is something which is related to fire, heat or temperature. So when because of the heat or temperature you are getting polarization, that is pyroelectric materials. Ferro, whenever you see this word, you understand it is talking about hysteresis curve. We will discuss what is hysteresis curve. So whenever ferro is there, there will be hysteresis curve. Gajendra Singh is asking, sir, I have prepared maths, aptitude, environment, quality and safety. Can I clear cutoff of GS paper? Definitely, why not? And I don't understand why don't you prepare all the subjects? Okay. just remove this lethargy from your mind. Just remove this laziness from your mind for next 1 week. As much as you can, just revise the things. Whatever you have completed properly, that is a good thing. But what you are leaving is not a good sign. Okay? Still time is there. You can attend the marathon sessions. You get the PDF, revise them 1 or 2 times before entering the examination hall. You will be in a better situation. Is it clear, everybody? And we'll talk about anti-ferro also. So let me first talk about the piezoelectric materials. Just a moment. Now basically the piezoelectric materials are those materials, if you apply the mechanical stress, mechanical force or pressure, then these materials will get polarized. Okay? You apply the mechanical force, mechanical pressure, mechanical stress, these materials will get polarized. Vice versa is also true. If you apply the electric field across them, then their physical dimensions are going to be changed. They are going to be strained. You understand? Stress and strain. So, we are defining the piezoelectric materials as materials which get polarized because of the application of mechanical stress are called piezoelectric materials. Getting polarized because of the application of mechanical stress are called piezoelectric materials. Now the reverse is also true. With the application of electric field, these materials get strained. It means strain produces directly proportional to the applied field. So what is the meaning of strain? Strain means changes or modifications in the dimension of the material. Is it clear? Now, these two phenomena are defined as direct effect and inverse effect. What is direct effect? When you apply the mechanical stress, there will be polarization. The example is microphone. What is the inverse effect? If you apply the electric field, you will get the strain. What is the application? Quartz watches. So the examples are quartz, barium titanate, BaTiO3, this is the most famous one. PbTiO3, lead titanate, PbZrO3, lead zirconate, then Rochely salt. Okay. Now let us talk about the expression for induced voltage in case of a piezoelectric material. So what is happening? Suppose you have a specimen, and this specimen, if you apply the pressure or the force, then some charges are going to be induced. How these charges are induced? So for the first thing we can say is that the charges induced is going to be directly proportional to the applied force. Yes or no? This Q is the total charge which is induced and F is the force. Now we are using one parameter D, which is defined as the charge sensitivity. Charge sensitivity means for unit amount of force, if F becomes 1, then how much charge is going to be developed? So for the unit force, how much charge is appearing across the surfaces, that will be defined as D. Is it clear, everybody? Now you can define Q as C into V. C is the capacitance and V is the voltage. D is the charge sensitivity. And how you can, okay, let it be force only. Now this capacitance C you can write as epsilon A by D. And this is V. And let me write it not D here. Okay, let me use another. Let me use another term here. Okay, suppose this is T. T is the separation. Okay, suppose this is T. This is T. Okay, So we will write the capacitance as epsilon naught A upon T. This is V and this is D and this is F. So what I will do, I will take this area inside the force. So it will become V upon, this will be V upon T, okay. And then you will be having force upon area. This is force upon area. And then you will be having D upon epsilon naught. This is D upon epsilon naught. Please check everything is okay. What is this V by T? This V by T, it will become, okay, let it be. Don't make it V by T. Don't write it in terms of the electric field. Just write it like this only, because we want to know what is the voltage developed across it. So this V is going to be force upon area. This is D, this is T, and this is epsilon naught. This is epsilon naught. Is it clear? So this we are defining as, suppose I am using this F by P as the pressure P and D upon epsilon with a new term G, and this is T is the thickness. So V becomes P into G into T. Now, where G is defined as the voltage sensitivity, where G is defined as the voltage sensitivity. I think last year or last to last year there was a question on this formula. So they can ask you this. So please remember this very simple, very easy formula PGT. P stands for pressure, G stands for voltage sensitivity, and T stands for thickness. You can understand, I will take around 2 hours, maybe 2.5 hours to complete it. So Dheeraj sir has left somewhere around 1, okay. So I think it is going to be around 3:30 or 4. 3:30 or 4. Is it clear, everybody? Now the next phenomena is electrorestriction. Now electrorestriction is a similar phenomena to that of piezoelectric materials or piezoelectricity, but it is not vice versa. It means what? Electrorestriction means there are some materials which develop some mechanical deformation, that is strain, when the external electric field is applied. But the reverse is not true. It is not that if you apply the mechanical stress, they will get polarized. No, that is the case for piezoelectric materials. In case of electrorestriction, only the application of electric field will develop the mechanical strain, that is the deformation. But the reverse is not true. Exhibit the electrorestriction phenomena. Now the strain produced, deformation produced is directly proportional to the square of the external electric field. Now we have pyroelectric material. I told you whenever you see this term pyro stands for fire, temperature, heat. So what is happening here? Listen carefully. These materials, they develop some polarization of the charge when there is a change in the temperature. When there is a change in the temperature, these materials get polarization. Now these materials exhibit spontaneous polarization. Now what is spontaneous polarization? Please understand. Spontaneous polarization is defined by two conditions. Number one, external electric field is 0, but polarization is not 0. It means even when there is no electric field present, still the material has some amount of polarization. This is called as spontaneous polarization. Is it clear, everybody? Okay. So E is 0, whereas P is non-zero. But the problem is the direction of polarization cannot be reversed. This is very, very important. You may get a statement-wise question on this statement. In case of pyroelectric material, the direction of polarization cannot be reversed by reversing the direction of electric field. So what is happening? As the temperature is increased, there will be thermal agitation, which will lead to reduction in the dipole polarization. The best example is barium titanate. Is it clear? Okay, now see. The pyroelectric material will develop some voltage, because when you say material gets polarized, it means there is a charge induced. So charge induced means there will be some voltage across it due to change in the temperature. Now even if the temperature is kept at this new value, slowly the voltage will disappear because of the leakage current. So it is of no use, because whatever voltage is developed because of the change in the temperature, it's not stable. Even if you keep the temperature at the new level, it is going to be reduced to zero. Whereas in case of thermoelectric effect, if you remember in your physics, you must have read this thermoelectric effect. Thermoelectric effect means because of the hot and cold junction, because of the temperature difference, there used to be a current induced in the circuit, that is called as thermoelectric effect, and that voltage induced or current is stable. That is, the two ends of the materials are kept at two different temperature or the junction, so that there is a permanent voltage across the material. So we are defining the spontaneous polarization. As I have already told you, spontaneous polarization in the most simple term you can understand, when the external electric field is zero but still the polarization is non-zero. When the material shows polarization even in the absence of external electric field, that is called as spontaneous polarization. Is it clear, everybody? Ferroelectric material, I told you ferroelectric material, wherever you have this term ferro, you understand it is going to have the hysteresis curve. So these materials exhibit the hysteresis curve and they have a spontaneous polarization. But the difference between ferroelectric material and the pyroelectric material is that pyroelectric material were also having the spontaneous polarization, but there is a difference. What is the difference? The difference is, if you see for the pyroelectric materials, the direction of polarization cannot be reversed by reversing the direction of electric field, whereas this is possible in case of ferroelectric material. The direction of polarization can be reversed by reversing the direction of external electric field. Now these materials exhibit the ferroelectric effect up to a certain temperature. That certain critical temperature is called as Curie temperature. Okay, up to the Curie temperature, on the basis, on the name of the scientist, the temperature is named as Curie temperature. The material is going to exhibit the ferroelectric effect. Now above the Curie temperature, the material will start behaving as a piezoelectric material. Now please understand, ferroelectric effect is like Mentos Zindagi. Are you getting this? You remember the example? Ferroelectric behavior is like Mentos Zindagi, and piezoelectric is like normal Zindagi, normal life. कमेंट तो करो भाई, कम से कम पता तो चले कि आप लोग फॉलो कर रहे हो कि नहीं. नहीं पढ़ना है तो बंद कर देते हैं. अगर नहीं मजा आ रहा है तो बंद कर देते हैं. आप भी मजे में, मैं भी मजे में. So ferroelectric behavior is like Mentos Zindagi, which is only available up to a critical temperature. Beyond that temperature, okay, they will start behaving like a piezoelectric behavior, that is Aam Zindagi. So let us understand with respect to this hysteresis curve, and please listen to me very carefully. Within one go, you will understand everything. Hysteresis curve is the relation between the polarization and the external electric field. Suppose this is the origin. You are starting from origin. Slowly you are increasing the electric field. You are increasing the electric field in the positive direction or particular direction. Is it clear? Now what will happen? If you increase the electric field, the polarization will increase in the material, something like this. But at some point, the polarization becomes saturated. Even if beyond this point A, if you increase the electric field, there will be no increase in the polarization. Why? Because suppose एक क्लास में 100 बच्चे हैं और मैं गया क्लास में, जैसे ही मैंने एंटर किया 100 के 100 बच्चे खड़े हो गए, उन्होंने मुझे रिस्पेक्ट दी. अब मैं गुस्सा कर रहा हूँ स्टेज पे जाके, और बच्चे क्यों नहीं खड़े हो रहे हैं, और बच्चे, भैया जब क्लास में बच्चे ही 100 हैं तो और कहाँ से खड़े हो जाए. And that is what is happening to your material. When all the dipoles will get oriented in the direction of electric field and there is no more dipole to be oriented, then there will be saturation. You keep on increasing the electric field, there will be no further increase in the polarization. So this point A is defined as the point of saturation. The point of saturation. Now at this point A, again if you start reducing the electric field or you start increasing the electric field in the opposite direction, what will happen? Again the polarization will reduce, but not at the same rate, but with some other rate. And you will reach point B. What is point B? At point B, now the field has become 0, origin. Field has become 0. But still you are getting some amount of polarization. This polarization is defined as residual polarization, बचा हुआ polarization, residual polarization or spontaneous polarization or remnant polarization, etc. Now, this spontaneous polarization, if you want to make 0, so what you will do? Now you will increase the electric field in the opposite direction, in the negative direction. So when you increase the field in the opposite direction, there will be one point C. At this point C, what happens? Now this spontaneous polarization is 0. Polarization is 0 here. But the amount of electric field that you have applied in the opposite direction, this is called as coercive field. This is defined as coercive field or coercivity. Coercivity. Is it clear, everybody? So further, if you increase in the negative direction, you will follow this curve, something like this. And this will keep on happening and you will get a closed curve. This curve is defined as the hysteresis curve. Is it clear, everybody? I think there should be no doubt here. I am assuming there is no doubt here. So this is the explanation for the hysteresis curve that I have already explained, so I am leaving it. Okay. So and this hysteresis curve will be present when the temperature is less than theta, that is the Curie temperature. That is the critical temperature, Curie temperature. You will get the Mentos zindagi. Now, when temperature is more than theta, that is the Curie temperature, again the material will start behaving as the piezoelectric material. And now the hysteresis curve is going to be represented by the hysteresis line. Okay. Now the hysteresis curve is going to be represented by a straight line. Is it clear? Something like this. For temperature more than theta, that is the, just a moment. No. Okay. So when temperature is more than this, the hysteresis curve will shrink into a straight line. Listen very carefully. Now the Curie temperature, the polarization is directly proportional to the applied electric field, and this relationship is governed by Curie-Weiss law. This relationship is governed by Curie-Weiss law. You don't need to go into the derivation part. That is for the core student that I will be discussing in maybe tomorrow or day after tomorrow session. I am planning that session. But for you, that derivations are not required here. What is required, I am giving you. Is it clear? So what is this Curie-Weiss law? This Curie-Weiss law says the polarization of the piezoelectric material can be assumed to be dominantly orientational polarization. Okay. So the piezoelectric behavior will be represented by this part when the temperature is more than theta. This is the Curie temperature, and when the temperature is less than theta, that is the ferroelectric behavior. This is going to be your electrical susceptibility Xi E plotted with respect to the temperature. Is it clear, everybody? Okay, those derivations are not required for you. You can avoid them very safely. So I will just give you the Curie-Weiss law. That is, this is going to be C upon T minus theta. Okay. This is the electrical susceptibility and how it is related. Is it clear? So if you see, when you increase the temperature, Xi is reducing, and that is what is happening with the piezoelectric behavior. That is governed by the Curie-Weiss law. For the ferroelectric behavior, there is a reverse phenomena. Up to the Curie temperature, if you increase the temperature, the susceptibility is increasing. What is the meaning of susceptibility increasing or decreasing? Yes, I will discuss about magnetic materials also. Actually, there is quite a similarity between the properties of the dielectric materials and the magnetic materials, but there are some difference in terms of way the properties of the physical phenomena are represented. Why not? You can expect numerical from electrical part also. Electrical electronics part, yes or no? Why not? From anywhere you can, we are discussing so many equations. I think you missed the starting part of the discussion. Okay, you may get question on that. The examples of ferroelectric materials are, okay, Rochley salt, barium titanate, lead titanate, KDP, disodium phosphate, alums, sodium nitrate, etc. Let us talk about the ferroelectric domains. Very interesting theory. Okay, very interesting theory, quite relatable. What is ferroelectric domains? Now the behavior of the ferroelectric material is very interesting. How to define it? So please understand what is happening. In the ferroelectric material, there are certain regions which are called domains. Now within these regions, all the dipoles are oriented in a unique fashion. Suppose if this is a region, so in this region, whatever dipoles are present, they are oriented in one unique direction. If you go to the other region, other domain, they are oriented in another direction. But within a region, all the dipoles are parallel to each other in the unique direction. So what happens? Because of this, and these are domain walls. These are called as domain walls. Now because of this reason, okay, ferroelectric domains, even in the absence of electric field, there is some polarization present. That is the reason they represent a spontaneous polarization. Even when electric field is zero, polarization is non-zero. Now what happens if you apply the electric field? If you apply the electric field, these domains walls are going to be collapsed and all the dipoles are going to be again oriented in the direction of external electric field, and you will get a very strong polarization in the material. Is it clear? Is it clear, everybody? Let us come to the anti-ferroelectric material. Anti-ferroelectric material. Anti-ferro, the name itself tells you that dipoles are parallel to each other, but they are in the opposite direction. Equal magnitude, but opposite direction. So definitely 100% you can say the spontaneous polarization has to be zero. When the dipoles are anti-parallel, magnitude same, anti-parallel, so their net effect is zero, so spontaneous polarization is 100% zero. Now up to the Curie temperature, again up to the Curie temperature, it is Mentos Zindagi. You will get the anti-ferroelectric behavior. You will get the anti-ferroelectric behavior. And beyond the Curie temperature, again there will be normal Zindagi, Aam Zindagi, piezoelectric material. The examples are lead zirconate, sodium niobate. I hope it is clear. If you do the comparison between the pyro, ferro and piezoelectric materials, then you can understand that the most general class of material is going to be piezo. Now, there are some piezoelectric materials which have pyroelectric properties also, and there are some piezoelectric materials which have pyroelectric properties also. At the same time, they are having ferroelectric properties also. So, you can say all ferro are pyro and piezo, or you can say all pyro are piezo materials. These are the two conclusions you may get in the form of question statement. Important. Is it clear, everybody? Now let us talk about the paraelectric materials. It is similar to the concept. You have paramagnetic materials in the magnetic materials. Paraelectric materials. Paraelectric materials are those materials which contains permanent dipoles, but because of the random orientation of the permanent dipoles, the resultant spontaneous polarization is again 0. It means for paraelectric materials also, there is no spontaneous polarization. Now, if you apply the external electric field, all the dipoles will align in the direction of field, and this will result in non-zero polarization. The example is ceramic materials. The example is ceramic materials. Is it clear, everybody? So, the last part we are discussing for the dielectric material, that is dielectric losses. You may get a question on this, so it is important, and then we will be talking about magnetic materials. Now, till now, if you have a doubt, you can ask me. Everybody? Till now, if you have a doubt, you can ask me. See. So, if you talk about the dielectric loss, why dielectric loss is happening? Suppose this is a dielectric material. Now, suppose AC supply is connected here. So, AC supply is going to be alternating with some frequency F. So, the potential which is appearing, or the electric field which is appearing across this dielectric, its polarity is going to be changed. Sometimes positive, sometimes negative, sometimes here positive, here negative. Yes or no? Now, because of the frequent reversal of the applied electric field or the voltage, the dipoles inside this dielectric material are going to be reversed frequently. So, the frequent reversal of the dipoles leads to a loss that we are characterizing or defining as dielectric loss. Is it clear, everybody? Just tell me yes or no. So, suppose you have a situation, you represent this dielectric with a parallel combination of a resistance to represent the loss and a capacitance, something like this. This is R and this is C. Total current is I. In the resistive part, suppose it is I1. In capacitive part, it is I2. So, if you define I1, current in the equivalent R, I2, current in the equivalent C, power loss is defined as VI cos theta, where theta is, this is I1, this is I2, this is the total current. Theta is defined as the power factor angle, because this I1 and V are going to be in the same phase because it is for the resistive branch. Yes or no? So, this theta angle is actually the angle between the total voltage and total current. So, this is the power factor angle. So, you are defining the total loss as VI cos theta. Now, theta you can write as del. Del is defined as loss tangent angle. Loss tangent angle. Okay. Loss tangent is defined as tan del. We will discuss about it. This is defined as loss tangent. Loss tangent. So, if you put theta as 90 minus del, it is going to be VI sin del. Now, how you can write in terms of I? How you can write in terms of I? So, you can write I2 cos del as capital I. Yes or no? Yes, here it is written. So, I2 you can write as I cos del or I you can write as, sorry, something wrong I have done. It is I cos del, sorry. It is I cos del. You take the projection of I here. I cos del is I2. I cos del is I2. So what is I? I becomes I2 upon cos del. So dielectric loss becomes V into I2 upon cos del. Now sin del upon cos del become tan del. It is the loss tangent. I2 again you can define as V upon XC, where XC is 1 upon 2 pi f into c. So it will be reversed and it will go to the numerator. So it will become I2 is V into 2 pi f c. So if you put the value, loss becomes V square 2 pi f c tan del watts. Is it clear, everybody? Is it clear, everybody? Tell me yes or no in the comment section. Say yes or no. Is it clear, everybody? Leave this, okay? This is for the comparison purpose, not required. This is for the comparison purpose, not required. Okay, this also you can leave. So let us start with the magnetic materials. We are starting with the parameters of magnetic materials. How we are starting? So there are basically three parameters of magnetic materials. Number one is permeability, then we have magnetic dipole moment, then we have magnetization. Okay, it is quite similar to what we have discussed for the dielectric. So there is going to be some similarity, but you have to understand the differences. That is important. Let me first talk about the permeability. How you are defining the permeability? Permeability is defined as the ratio of magnetic field density and the magnetic field intensity. So mu you can again define as mu naught mu r, where mu r is the relative permeability and mu naught is defined as the permeability of the free space, whose value having the value as 4 pi into 10 to the power minus 7. You remember that? 4 pi into 10 to the power minus 7. This is already mentioned here. Let us talk about the magnetic dipole moment. We have discussed for the electric dipole moment. Now let us talk about the magnetic dipole moment. Yes, Payash. Please understand, if I give you a bar magnet, this is north pole, this is south pole, and I ask you to separate this north pole and south pole. So what you will do? You will bring something to cut it. You will cut it from here. Now you will be getting portions like this. Yes or no? But what do you feel? It will be separated? No. Again there will be a south pole, again there will be a north pole. It means for the magnetic field, monopoles do not exist. North pole cannot exist alone. Positive charge can exist alone. Negative charge can exist alone individually. Are you getting this? But for magnetic field, magnetic systems, north pole and south pole. So poles cannot exist independently. Wherever you have north pole, you will have equivalent south pole. Take the example of a current carrying coil. If you see this current carrying coil, suppose the current is flowing in the clockwise direction. How to find the direction of flux? Now rotate, use your right hand, rotate your fingers movement in the direction of current, that is clockwise, and the direction of thumb is going to give you the direction of magnetic flux. So it is into the plane of the screen. It is into the plane of the screen. So whenever flux travels from air to the core or coil, it is south pole. Whenever the flux travel, listen, how the flux is traveling. How the flux is traveling. Suppose this is a bar magnet, north to south. The flux is going to travel north pole to south pole. North pole to south pole, something like this. So when it is north pole, the flux is coming out from the core to the air gap or air. Yes or no? But when it is south pole, the flux is coming from air to the core. Air to the core. So when the flux is going into the plane of the screen, this is south. But if you have supernatural powers and anyhow you can go behind this screen and you can see what is the sense, current sense direction, and you find, then you will see the other side is going to represent the north pole. So one side of the coil is representing south pole, the other side as north pole. Yes, Maniket, what do you want to say? Everything is okay? Yes, north, south, north, south. Is it clear, everybody? Okay. So how we are defining? This is the magnetic dipole. Okay, you understand? A current carrying loop is defined as the magnetic dipole. A current carrying loop is defined as the magnetic dipole. Magnetic field monopoles do not exist. North and south pole cannot exist individually. Okay. Now, how we are defining the magnetic dipole moment? Current multiplied by the loop area. Current multiplied by the loop area, and it's a vector quantity. An is the normal area normal vector. An is the area normal vector, that is the normal to the area of the surface. Is it clear? This is how we define the magnetic dipole moment. Is it clear, everybody? Now the atomic unit of magnetic dipole moment is given as Bohr magnetron. How we are defining this Bohr magnetron? You may get a question. Suppose you have one electron revolving in a circular orbit around the nucleus having a radius r. So it is going to give the effect of a current. How we define current? Current is dq by dt. In dt time, how much charge is passed, that is defined as current. So I will be defined as the total charge passed is E. What is the time? Time period is 2 pi by omega. Yes or no? So just solve it. It becomes E omega upon 2 pi. I becomes E omega upon 2 pi. This is the current constituted. Then how you are writing the dipole moment? PB, it is I into A. I you can write E omega upon 2 pi. Area is pi r square for the loop. So if you simplify, it becomes PB becomes E omega r square by 2. E omega r square by 2. Now there is one small problem. We want to remove this omega. We are not interested in omega. Are you getting this? So how you can remove? Suppose this is the, just a moment. Suppose this is the electron, single electron orbiting in a circular orbit around the nucleus having a radius r. So what will happen? You can write the angular momentum by using the Bohr's theory. What is the Bohr's theory? Bohr's atomic model. Bohr is saying electron is not moving, orbiting in any random orbit. Electron can only be present in that orbit for which its angular momentum is conserved. Because if its angular momentum is conserved, it can orbit or it can revolve in the orbit without losing its energy. Remember that? That is the major, you can say, principle or insight given by Bohr, Bohr's atomic model. Because if the electrons are constantly moving, it must be losing the energy. So one day it will collapse into the nucleus. That was the problem. So Bohr said that it is not that any random orbit electron may be present. No, electron will only be present in that orbit for which its angular momentum is conserved. So conserve the angular momentum. MVR is the angular momentum is equal to NH upon 2 pi, where N is the principal quantum number, H is the Planck's constant, 2 pi, its value is given as 6.626 10 to the power minus 34 joules second. N is the principal quantum number, V is omega r. Just put the value of V as omega r. So you will get the value of omega. Just put the value of omega in the previous equation, E omega r square by 2. And finally, you will be getting the dipole moment as NEH upon 4 pi m. Now for one Bohr magnetron, this n has to be 1. So put the value of n as 1. E is electron charge is 1.6 10 to the power minus 19. H is Planck's constant. H 6.626 10 to the power minus 34. This is 4. Okay, this is 4. Wait. Okay, this is pi. This is 4 pi. This is 4 pi and mass of the electron is 9.1 into 10 to the power minus 31. So if you solve this, one Bohr magnetron you will be getting as 9.27 10 to the power 24 ampere meter square. Is it clear, everybody? Either you remember this or you remember this, EH upon 4 pi m. In examination, if you don't remember exactly, you can put the values. See the next one. Larmor's angular frequency. What is this Larmor's angular frequency? Now see what is happening when there is no electric field. When the electric field is, when the magnetic field is 0. We have to talk about magnetic field because we are talking about magnetic materials. So when there is no external magnetic field, suppose the angular frequency of the orbiting electron is omega naught. It is omega naught. But when external magnetic field is applied, what is happening? The angular frequency becomes from omega to omega dash, that is omega naught plus omega L. This is actually suffix. Omega dash is omega naught plus omega L. So omega L you can define as omega dash minus omega naught. This omega L is defined as Larmor's angular frequency. Magnetization. The same way we have defined the polarization, you can define the magnetization. It is the sum total of all the magnetic dipole moments per unit volume. So very easily you can write it, yes or no? Very easily you can write it. Number of magnetic dipoles per unit volume multiplied by individual dipole moment, PV. Is it clear, everybody? Just tell me yes or no. You guys are looking quite puzzled to me. If you want, you can take a small break. Because it will take some time. It is not going to be completed this soon. Okay. No issue. You take a 5-minute break and come to the class again with full energy. The time is somewhere around 2:48. Around 2:50, 2:55 we will start the class. Okay? Is it clear? So I can understand it's more than 4 hours. Okay? So take a 5 to 7 minutes break. Okay? But come back, okay? कसम खा के जाओ कि वापस आओगे. मजाक कर रहा हूँ, ठीक है? So we'll join soon. So guys, welcome back. I hope now you are completely fresh. Now we can start. So now we are talking about the magnetic materials and we were discussing about the magnetization, and I told you that as we were discussing about the polarization, similarly we are talking about the magnetization. It is the sum total of all the magnetic dipoles per unit volume of the material. That is how we define the magnetization. So M represents the magnetization of the material, N represents the number of magnetic dipoles per unit volume, and PB represents the magnetic dipole moment of individual dipole. Is it clear, everybody? We are going very basic. Is it clear? So now if you want to define the relation for the magnetic field intensity and the magnetization, the way we have defined the relation between the magnetic field intensity and the polarization, you can write that the total magnetic field density will have two components, mu naught H plus mu naught M. Mu naught H represents the magnetic field density or flux density due to the external field. External field is represented by H. It's something like this. Suppose you have a magnetic material and you apply some external magnetic field which is non-zero, and suppose all the magnetic dipoles, I am representing like this to make you understand better, they are aligned in the direction of external magnetic field. So I want to know what is going to be the B value. So how you can write? B becomes mu naught H plus mu naught M, where mu naught is the permeability of the free space. The second component, mu naught M, is the flux density due to the induced magnetization in the material. But you know that B is mu naught mu R H. So if you put it, mu naught mu R H is equal to mu naught H plus mu naught M. Mu naught will be cancelled and you will be simply getting M as mu R minus 1 H, and this we are defining with a new term, that is xi M, that is the magnetic susceptibility of the material. Magnetic susceptibility of the material. Is it clear? And what is the relation between susceptibility and the relative permeability? It is mu R minus 1. It is mu R minus 1. Already written here, mu R minus 1, magnetic susceptibility. Now the materials for which you have the positive value for the magnetic susceptibility, these materials are attracted by the magnetic field. So you can say these are going to be the magnets. You in general you talk about magnets, okay? But if you have a negative value for the magnetic susceptibility, the material is repelled away from the field. Now let us understand what is the origin of permanent magnetic dipole moment in the magnetic materials. How we are having the permanent magnets. Okay, you see there are some materials which are exhibiting spontaneous magnetization without the external magnetic field. They have their own magnetic field. How it is present, let us understand. So when a charged particle has angular momentum, it contributes to the permanent magnetic dipole moment. So whenever there is a charged particle which is rotating in approximately a circular path, it will have some angular momentum, and that angular momentum will contribute to the magnetic dipole moment. Now the permanent magnetic dipole moment may be due to the following three contributions. Number one, orbital electron angular momentum. It means if this is the nucleus, this is the orbit of the electron, and the electron is orbiting in this particular orbit. So this movement we are defining as orbital angular momentum, which contributes to the presence of permanent magnetic dipole due to the motion, orbital motion of the electron. Second is electron spin angular momentum. Now this electron is not just revolving, it's not just revolving in this orbit, at the same time it is spinning around its own axis. Okay, so this is electron spin angular momentum. Then we have nucleus spin angular momentum. Now this nucleus is also not stationary, and this nucleus is also going to be spinning around its own axis, so that is nuclear spin angular momentum. Now out of these three contributions, the electron spin angular momentum is the dominant one, which defines whether there is a permanent magnetic dipole moment present or not. Is it clear for everybody? Just tell me yes or no. So electron spin angular momentum is the deciding factor whether magnetic properties are there or not in case of magnetic materials. The electron spin angular momentum of elements of a completely filled orbit is 0. So if you have an element whose orbits are completely filled, for the completely filled orbits there will be no spin angular momentum. Whereas the elements having partially filled orbits, these are called transition elements. Now the transition elements will have electron spin angular momentum. For example, iron, manganese, I think this is Cr, chromium, selenium, titanium. For the iron, if you see, the atomic number is 26 and the electronic configuration is like this. So this is going to be the outermost orbit, that is 3d6. Okay. So because of this partially filled orbit, there will be electron spin angular momentum, which will be, yes, Mishra. Yes. Okay, so let us now talk about the classification of magnetic materials. So basically we have 5 types of magnetic materials, that is diamagnetic material, paramagnetic material, ferromagnetic material, antiferromagnetic and ferrimagnetic materials. Let us understand one by one. If you talk about the diamagnetic materials, these materials do not have permanent magnetic dipoles. Okay, and we will understand that diamagnetic materials which are having the perfect diamagnetism property, they are the best suited for superconductors. They are the same materials from which we make the superconductors. Now these materials have a small and negative value of magnetic susceptibility, small and negative value of the magnetic susceptibility. These materials are repelled away. Why they are repelled away? You will understand. They are repelled away from the magnetic field, and their magnetic susceptibility is independent of the temperature. It is not changing with the temperature. So if you see the diamagnetic material, it is the only magnetic material which is going to repel away, or you can say the magnetic lines are going to be bypassed. It is not penetrating. Whereas if you have paramagnetic, ferromagnetic, antiferromagnetic, okay, ferrimagnetic materials, if it is placed in an external magnetic field, the magnetic fields will converge into the magnetic material. For the diamagnetic material, if the magnetic flux density is 0, why it is 0? Because the magnetic field lines are repelled away. So they are not going to support the magnetic field. So B is 0. When B is 0, mu naught H plus mu naught M is 0, or M is equal to minus H. So what is, if you compare it with xi m H, so what is going to be xi m value? It is minus 1. So for a perfect diamagnetic material, the magnetic susceptibility is minus 1, which is equal to mu r minus 1, minus 1, minus 1 cancel. So for a perfect diamagnetic material, the relative permeability is going to be 0. Is it clear, everybody? Just tell me yes or no. mu r for a perfect diamagnetic material is 0. And this is the condition for superconductors. Perfect diamagnetism is the condition for superconductors. Is it clear, everybody? Just a minute. Is it clear, everybody? Okay. Hence, we can say for diamagnetic materials, mu r 0 is the condition for perfect diamagnetism, and this is a necessary condition for a material to be a superconductor. The examples of diamagnetic materials are copper, gold, germanium, silicon, diamond, sodium chloride, Al2O3, etc. Let us talk about the paramagnetic materials. Now, these materials, when they are placed in an external field, they acquire a weak magnetization in the direction of field. Why they get weak magnetization, we will discuss. When they are placed in the external electric field, they get weak magnetization. Therefore, these materials have a small and positive value of the magnetic susceptibility. These materials do not have any interaction between the dipole moments, so they are randomly oriented, and this is the reason they are getting the they are getting no spontaneous magnetization because they are randomly oriented, something like this. Okay, so the net magnetization will be 0 when there is no external electric field. Now, when a magnetic field is applied, these dipoles tend to align in the direction of the field, and if no opposing force is present, there will be a very strong magnetization. But there is a problem. What is the problem? But actually, due to the thermal agitation, because of the temperature, because of the thermal agitations, the dipoles remain randomly oriented, and this is the reason for the weak magnetization of the paramagnetic materials. Everybody just tell me in the comment section, are you able to follow this or not? So, if you increase the temperature, thermal agitation increases, susceptibility reduces. Let us talk about the Curie law. Some of the paramagnetic material, not all, there are some paramagnetic material which follow the Curie law. Curie law is simply given as xi m is equal to C upon T. I have given you the values for C, but I think you check it. Okay, this derivation is not required for you. For you, this much information is sufficient, that the Curie law says xi m is C by T, where C is a constant and its value is given here, but if you want, you can remember it, otherwise leave it, and T is the temperature. The examples are this. But there are some other paramagnetic materials which follow the Curie-Weiss law and they do not follow the Curie law, and this is given as, the derivation is here, but I would request you to only focus on this. Okay, Curie-Weiss law says xi m is C upon T minus theta. This is Curie-Weiss law. Okay. So, you see, when the temperature is less than the Curie temperature, the behavior is, it's not ferroelectric, it's ferromagnetic. Okay. And when temperature is more than theta, that is the Curie temperature, the behavior is paramagnetic. So, again you can understand this ferromagnetic behavior is the Mentos zindagi. Okay. This is the Mentos zindagi and paramagnetic is the Aam zindagi. Is it clear, everybody? Okay. So, this was the Curie-Weiss law. Okay. Upon T minus theta. This portion is represented by the Curie-Weiss law, C upon T minus theta. If you increase the temperature, the magnetic susceptibility will fall rapidly. Now, For the Curie law, we have Xi is C upon T. Again, if you increase the temperature, Xi will reduce, but here there is no transition temperature. There is no transition temperature. Okay, so this is Curie law. You understand from the diagram, it represents Curie-Weiss law, it represents Curie law. Or basically you can say materials which may represent ferromagnetic behavior up to the Curie temperature, and beyond that they represent paramagnetic behavior. Those materials follow Curie-Weiss law. And materials which does not represent the ferromagnetic behavior at all and they represent the paramagnetic behavior, they follow the Curie law. Is it clear, everybody? I hope it is clear. Ferromagnetic material. Wherever you get this term ferro, you understand it is going to be the hysteresis curve. Now these materials, the magnetic dipoles which are aligned parallel to each other. So you can understand with this diagram very easily that even in the absence of external magnetic field, a very strong magnetization will be present inside the material, and this is called as spontaneous magnetization. This is called as spontaneous magnetization. In short, you can write, even when the external field is zero, magnetization is non-zero. Is it clear, everybody? Yeah, something like this. Permanent dipoles parallel to each other, very strong spontaneous magnetization. Clear? Now once again, Mentos Zindagi and Aam Zindagi. So up to the Curie temperature, they are going to have ferromagnetic behavior. Up to the critical temperature called Curie temperature, they have the ferromagnetic behavior. Beyond this temperature, above the Curie temperature, they have normal Zindagi, Aam Zindagi, paramagnetic behavior. Once again, you can see this hysteresis curve. I think you will understand quite fast. For temperature less than theta, when it is the ferromagnetic behavior, the same process. I hope you remember just now in the same class I have explained. The only difference is here it is magnetization or magnetic field B, and here it is H. So A represents the saturation point, B represents retentivity. Retentivity means even if magnetic field is zero, how much is the remaining flux, remaining magnetization, or spontaneous magnetization, or residual magnetization, or residual magnetization. Residual magnetization. Okay, same thing, we have already discussed it. Now when the temperature is above the Curie temperature, again it is Aam Zindagi, so you are getting the paramagnetic behavior for temperature more than Curie temperature. So the hysteresis curve is going to be shrinked into a straight line. Let us talk about the antiferromagnetic behavior. As the name indicates, antiferro means the magnitudes of the permanent magnetic dipoles is same, but they are anti-parallel to each other. They are anti-parallel to each other. So definitely spontaneous magnetization will be 100% zero. Yes or no? They have anti-parallel alignment with the equal magnitude. So there will be no spontaneous magnetization. But this Mentos Zindagi anti-ferro behavior will be available only up to a critical temperature, which is called Néel temperature. This Néel temperature is not that Néel Nitin Mukesh, okay, he is not a scientist, okay, there is a different scientist named with Néel. So Néel temperature you remember for anti-ferro. Above the Néel temperature, again there is Aam Zindagi, the anti-ferromagnetic behavior will be gone and the material will represent the paramagnetic behavior. Is it clear? So due to anti-parallel alignment, in the absence of external field, the net magnetization is zero. It means if H is zero, then magnetization is also zero, and the relation between the magnetization and the field intensity is governed by the relation which is very similar to the Curie-Weiss law, but here there is a positive sign. Xi is C upon T plus theta n. Theta n is the Néel temperature, T is the temperature, C is the constant. These are the examples. These are the examples. Is it clear, everybody? Still, I am not getting the comments. Nobody love me, anybody, no problem. Ferrimagnetic behavior. Now, ferry, please remember, again, the magnetic dipoles are anti-parallel to each other, but the difference is here the dipoles are of unequal magnitude. Anti-parallel alignment, but of unequal magnitude. So, there will be spontaneous magnetization, yes or no? Even though it is small, but there will be spontaneous magnetization. Now, these materials represent net magnetization in a particular field even in the absence of external magnetic field. Hence, they represent the spontaneous magnetization. It means even if H is 0, M will be non-zero. Ferrimagnetic materials remain ferrimagnetic up to a critical temperature. Again, Mentos Zindagi is only up to Curie temperature, and above the Curie temperature, again, Aam Zindagi material start behaving as the paramagnetic material. Okay. Now, one of the big advantage of these material is that they have high DC resistivity. High DC resistivity, and this is the reason at the high frequency, if you have to operate your transformer, the core of the transformer is made of ferrimagnetic material. Okay, electrical guys must be understanding this. Because of the high DC resistivity, it is used. Now, therefore, they have lesser eddy current losses in comparison to the ferromagnetic material, and therefore, ferrites or the ferrimagnetic material are used as the core of the transformers on inductive coils at high frequency, because high frequency the eddy currents or eddy current losses are going to be very significant. Properties of the ferrites: they have high DC resistivity, low eddy currents, high permeability, high dielectric constant, high Curie temperature, extremely low dielectric losses. Okay, I hope you understand this. Now, the classification of the ferrites on the basis of their application. So, basically we have hard ferrites, soft ferrite, rectangular ferrites. It is ferrites, not fomites. Okay. Okay. So, rectangular ferrites, they are basically used for magnetic memory, because their BH curve is something like this. It's rectangular. Okay, so it is maybe something like this. Okay, so because of this rectangular BH curve, rectangular ferrites are used for magnetic memory. Now, definitely microwave ferrites are going to be used at the microwave frequency. What about hard ferrites and soft ferrites? Hard ferrites, they are used for permanent magnet application. Now, for the hard ferrite, these materials must have high coercive field. High coercive field, it means something like this. Their hysteresis curve is going to be something like this. This is B, this is H. Are you getting this? So, they are going to have this coercivity has to be high for hard magnetic materials. Sorry, coercivity is also high, and retentivity. It represents retentivity. Retentivity is also high, and coercivity is also high. In order to make the permanent magnets, we are using the hard ferrites. For example, barium and strontium ferrites. For soft ferrites, they have low value of coercive field. So, for soft ferrites, the BH curve is going to look something like this. Okay. It is going to be something like this. Okay. Yes, both high. Is it clear? So here the coercivity and the retentivity both are small. So they are preferred as the core material for the transformer at high frequency. Magnesium, manganese and zinc ferrites, nickel and zinc ferrites, TV and audio transformers. Rectangular ferrites, I told you these materials have rectangular hysteresis curve, so they are used in the magnetic memories. These are the examples. Then we have microwave ferrites. Now these ferrites are basically used at the microwave frequency. Now see why these ferrites are used at the microwave frequency. What is the reason behind it? Let us understand. What happens at the very high frequency, at microwave frequency, the polarization of electromagnetic wave may lead to the rotation of electromagnetic wave polarization by some angle. This phenomena is known as Faraday's rotation. Now, what is the polarization of electromagnetic wave? First, understand the electromagnetic wave. An electromagnetic wave is defined as a wave which has electric field also, magnetic field also, and P defines the Poynting vector. Poynting vector which represents E cross H, which represents the direction in which the electromagnetic wave is traveling. Okay. But for this electromagnetic wave, electric field E defines the polarization. Okay. Because the magnetic field is solenoidal, but electric field is divergent. So electric field defines the polarization. So what happens? Because of high frequency, there is a possibility that the spin angular momentum may interact, it's not interest, it interact with the polarization of the EM wave, leading to the rotation of EM wave polarization by some angle. This is called as Faraday's rotation. This may be asked. Is it clear, everybody? Magnetic anisotropy. So anisotropy we have already discussed when the properties are dependent upon a particular direction of observation. This direction property is different, this direction property is different, then it is, this property is called as anisotropy. Now if in a magnetic material different magnetization is achieved by the application of magnetic field in different directions. So different directions, property is different. This property is known as magnetic anisotropy. So there are basically three methods from which it can be achieved. For example, cold working. Cold working such as cold rolling brings some regularities in the orientation of the unit cell, and this help in achieving a large value of magnetization. Okay, this is a theoretical part. The best example is cold rolled grain oriented steel, CRGO steel. Okay, one method I think I have missed, so let me take it down. Just a moment. Rectangular ferrite, microwave ferrite, all done. Yes. The second one is magnetic annealing. Okay. Second one is magnetic annealing. Now first cold working we have discussed. Now magnetic annealing is represented by slow heating and slow cooling. Slow heating and slow cooling. Examples I can give you. Okay. No problem. Leave the example side now. Magnetic quenching. Okay. There is some problem. We can write the second method here. Slow heating and slow cooling. Third is magnetic quenching. As the name indicates, the metal is fast. Metal has fast cooling in the presence of magnetic field through the Curie temperature, leading to a uniaxial anisotropy, either parallel or perpendicular to the field. So fast cooling in the presence of magnetic field. Magnetostriction. Magnetostriction is a phenomena that we have discussed for electric. We have discussed for dielectric materials also. That is electrostriction. So what happens? Because of the application of the magnetic field, there is a mechanical strain produced in the magnetic material, and the best example that you can understand is, if you stand near a transformer, you will listen a constant hissing noise. Some noise is coming like that, na? Constant. What is that noise? That noise is because of magnetostriction. Because of the alternating nature of the current flowing in the windings, these are having fluctuating magnetic fields, because of which there is a mechanical strain produced in the physical dimension of the magnetic material. This is known as magnetostriction. There are basically three types of magnetostriction: longitudinal, transverse and volume. Longitudinal means if the dimension of the magnetic material changes in the direction of magnetization, then it is longitudinal. If the dimension of magnetic material changes in the direction perpendicular to the direction of magnetization, then it is transverse. And volume, when both perpendicular and parallel to the magnetization, then it is volume magnetostriction. The last one we have is the Villari effect. It is the converse. It means the reverse of magnetostriction. It means if you apply the mechanical stress or force or pressure, then there will be some magnetization present. That is called as Villari effect. Is also observed in magnetic materials where a longitudinal deformation leads to a change in the permeability in the direction of applied strain. So now let us talk about superconductors very fast. This is the last part we are discussing. So it's already 3:30. I think just not more than 15 minutes I will take to finish it up. Only major points I am focusing. Is it clear? Everybody is clear? Everybody tell me. So superconductors, how we are defining? Suppose you have a superconducting coil. So ideally it says that for superconductors the resistance is 0. When resistance is 0, and if you anyhow manage to allow a current to circulate in a closed coil, then because it is a superconducting material, then this current will be circulated up to infinite time, because there are no losses. So these materials which exhibit zero resistivity or zero resistance, they are called superconductors. Now there are some materials which are non-superconductors. So if you increase the temperature, their resistance or the resistivity will increase. But there are some materials which behave like a superconductor. So what happens? Beyond a critical temperature, it means below the critical temperature, the resistance is 0. But beyond this temperature, more than this temperature, it has the normal behavior like any other conductor. Are you getting that? So more than the critical temperature, normal behavior. Less than the critical temperature, it is superconductor behavior. Now this transition is reversible. When the temperature is more than critical temperature, then it goes to normal state. When the temperature becomes less than critical temperature, then it comes into superconducting state. Now what is Meissner effect? We have already discussed it when we were discussing the diamagnetism, that it is the repulsion of the magnetic flux from the inside of the material. And that is why I said the perfect diamagnetism is the necessary condition for any material to be a superconductor. So he is saying when the repulsion of the magnetic flux happens from inside of the superconducting material, as the material undergoes the transition to the superconductivity, this phenomena is known as Meissner effect. Like this. I hope you remember the diamagnetic materials. Yes or no? Now this, we can define the critical field. Just a moment. Yes. Critical field we are defining as 1 minus T upon Tc whole square something like this. Okay. Where H naught is the critical field. H naught is the critical field at 0 degree Kelvin, and Tc is the critical temperature, and Hc is the critical field at critical temperature Tc. This is the relation. So you can observe from this that if you increase the magnetic field, the critical field, then for corresponding critical field, the critical temperature is going to be less. Are you getting this or not? Is it clear? What is Silsby's rule? Silsby's rule says that if you allow a conductor to pass a current which produces a magnetic field which is equivalent to the critical field of the material, so that the superconductivity is gone. This phenomena is defined as Silsby's rule. मतलब एक कंडक्टर है, उसमें आपने ऐसी करंट फ्लो कराई कि उसकी वजह से जो मैग्नेटिक फील्ड डेवलप हुई वो क्रिटिकल फील्ड के बराबर था, तो सुपर कंडक्टिविटी चली जाएगी, खत्म हो जाएगी. Is it clear, everybody? Okay. So what I was saying, yes, if a superconducting material carries a current such that magnetic field it produces is equal to the critical field, the superconductivity disappears. This is called Silsby's rule. Let us talk about the types of superconductors. So basically we have type 1 superconductor, type 2 superconductor. Type 1 superconductor, these are called ideal or soft superconductors. Their critical temperature and critical field are low values. The change in the state is abrupt from normal state to superconducting state, and they exhibit Meissner effect and Silsby's rule. These are the examples. Now if you see in terms of the magnetization, okay, the transition from superconductor to normal state is sudden. It's sudden. If you see in terms of the resistivity, superconducting state, resistivity 0, normal state, suddenly within no time it will make a transition from normal state to superconducting or superconducting state to normal state. If we talk about the type 2 superconductor, they are ideal or hard superconductors. Type 1 was soft superconductors. Their critical temperature and critical field, they have high values, whereas for type 1 it was low value. Now the change in state is not abrupt, it is gradual. It's not that it is going from 0 to 1, 0, 0.1, 0.2, 0.3 up to 0.9, then 1. Now they exhibit incomplete, it means they are partially representing the Meissner effect and Salisbury's rule. For example, if you see the magnetization and field curve, you will see from the superconducting state, it is not directly going to the non-superconducting state or normal state. There is a transition. This transition region is called as intermediate or vortex region. Intermediate or vortex region. Similarly, you can see in terms of just a moment, some misprint is there. Just a moment. So what is happening? If you see in terms of the resistivity, you will observe that resistivity is 0 here when it is the superconducting state. Now from the superconducting state to the normal state, the transition is smooth. Yeah, it changes gradually, not the abruptly, from here to here. Again, this is called the vortex region. Is it clear, everybody? So this is all from my side for today's session. I hope you enjoyed the session. And before I leave for today, let me tell you that where the PDF is going to be available. For my side, the PDF will be available on my personal Telegram channel on BYJU'S exam prep. That is, I will be writing in capital. That is Electrical by Ashutosh Saxena. Electrical by Okay. So thank you so much, friends, and stay connected. I have already talks with the backend team, so I am planning 2 sessions. One for the ethics second part may be planned tomorrow or day after tomorrow. So stay connected, and I want all of you to be there in that session live. I will be updating the timings and the date right on my Telegram channel. So be aware, be alert, so that you do not miss this. So thank you, friends. Take care. And before I conclude, once again, 15th of February, when the GATE responses are going to be available, you can know your GATE 2023 rank by using the BYJU'S exam prep rank predictor. You have to register yourself to avail this, because hundreds, thousands and lakhs of candidates are going to use this. So you will get a better idea about your rank, so that you can take better decisions. Yeah, we'll be, both of us, me and Dheeraj sir, will be sharing the respective links for the Telegram channel in the comment section of this video when the video is in the recorded form. So everybody, before you leave, hit the like button, show your love, hit the bell icon and subscribe to BYJU'S exam prep for all important sessions. Thank you so much. Take care. Thank you, everybody. Thank you. All the best.